Imagine the world had finally found its rhythm. After the last ice age loosened its grip, after thousands of years of chaos and cold, humans had figured something out. They'd started staying in one place, planting seeds, building homes that lasted longer than a season. Farming was spreading. Villages were growing into something like permanent communities for the first time in the entire history of our species. The climate was warm, stable, generous. It felt like the hard part was over. Then, 8,200 years ago, something happened that nobody saw coming. Temperatures dropped, fast, not over centuries, but within a human lifetime, maybe less. Rainfall patterns that farmers had come to depend on shifted or vanished entirely. In some regions, decades of careful progress, the slow accumulation of knowledge about when to plant, where to settle, how to survive, all of it got tested against a climate that no longer played by the old rules. Scientists today call it the 8.2 kiloyear event, or simply the 82K event. And even now, with all our satellites and sensors and supercomputers, we're still piecing together exactly what it did to the people who lived through it. Here's the question that should keep you gently curious tonight. If you built your entire way of life around a stable climate, and then that stability just disappeared, what would you do? Would you move? Would you dig in and adapt? Would you start believing that the gods were angry, that something needed to change not just in your fields but in your rituals, your leadership, your entire understanding of the world? Because that's exactly the position early farming communities found themselves in when this cold shock rippled across the planet. Tonight, we're going to trace that ripple. From the ice sheets of Canada to the villages of the Near East, from the Nile to the monsoon systems of South Asia, we're going to follow one abrupt climate event and ask how it may have quietly reshaped the trajectory of early civilization. Not through catastrophe and collapse necessarily, but maybe through something more subtle. Adaptation, innovation, the kinds of small human decisions that, generation after generation, add up to entirely new ways of living together. Before we go further, if you're listening to this to help you fall asleep, that's exactly why I make these. So tell me, where are you right now, and what time is it for you? I love checking the comments and seeing this strange little map of the world. Someone in Sydney getting ready for their morning coffee, while someone in Chicago is drifting off at midnight, all listening to the same story about ice cores and ancient rivers at completely different hours. And if these histories help you unwind, the best way to support what I do is completely free. Follow the show on Spotify, and if you have a moment, leave a 5-star review. There's a link in the description. It genuinely helps more people find these stories, and more importantly, it helps more people sleep. So settle in. We're about to travel back to a warm world that suddenly, briefly, turned cold. And we're going to see just how thin the line really was between stress and transformation. Let's rewind a little further, past the shock itself, back to the centuries that made the shock possible in the first place. Because to understand why 8,200 years ago mattered so much, you have to understand what the world looked like right before it happened. And what it looked like was recovery. Slow, patient, almost miraculous recovery. Around 11,700 years ago, the last ice age finally released its grip on the planet. Not instantly, not smoothly, but the great ice sheets that had buried much of North America and Europe under kilometers of frozen weight began their long retreat. Temperatures climbed. Sea levels rose. Landscapes that had been locked in permafrost or buried under glaciers slowly transformed into forests, grasslands, wetlands. This new era, the one we're still living in today, geologists call the Holocene. And for the first several thousand years of it, something remarkable happened. The climate settled down. Not perfectly, never perfectly, but compared to the wild temperature swings of the Ice Age, Compared to the abrupt warm and cold oscillations that had characterized the previous tens of thousands of years, the early Holocene was relatively calm, predictable, the kind of climate where a farmer could plant a seed in spring with some reasonable confidence about what summer and autumn would bring. That kind of predictability had never really existed before. Not like this, not for this long, and that stability mattered more than almost anything else in human history, because stability is the invisible foundation underneath agriculture. Think about what it actually takes to be a farmer instead of a forager. You have to commit to a location. You have to invest months of labour into fields you won't harvest until much later. You have to trust that the rains will come when they're supposed to come, that the river will flood when it's supposed to flood, that the seasons will behave the way they behaved last year and the year before that. Foragers can move when things go wrong. They can chase the rain, follow the herds, shift territory when conditions shift. Farmers, by contrast, are betting everything on the ground beneath their feet, staying reliable. It's a bet against uncertainty, and for the bet to work, the uncertainty actually has to be low. For a few thousand years after the ice retreated, it was. This is the backdrop against which some of the most important experiments in human history were unfolding. In the Fertile Crescent, stretching across what's now Iraq, Syria, Turkey and the Levant, communities were domesticating wheat and barley, lentils and peas, sheep and goats. Villages that had once been seasonal camps were becoming permanent settlements with mud brick houses, storage pits, shared spaces for gathering and ritual. Some of these places would eventually grow into the first true towns anywhere on Earth. Meanwhile, similar experiments in food production were beginning to take shape elsewhere, though usually a little later and along different timelines. In parts of East Asia, communities were beginning to cultivate rice and millet. In the Americas, wild plants were slowly being coaxed toward domestication. Though full agricultural societies, they were still a long way off. Across North Africa, in a Sahara that looked almost nothing like the desert we know today, monsoon rains had pushed much further north, creating lakes, rivers and grasslands where lions and hippos lived alongside human hunter-gatherers who were beginning to herd cattle. The whole world, in its own separate corners, seemed to be inching toward the same discovery, that a settled life, built on cultivated plants and managed animals, was possible, maybe even better than what came before. None of this happened because the climate was perfect. It happened because the climate was, for a while, good enough and steady enough for humans to plan around it. Generations could pass on knowledge. This is when we plant. This is where the water comes from. This is how we store grain through a bad year. That knowledge only has value if the rules of the environment stay roughly the same long enough for it to be tested, refined, and trusted. And that brings us to the strange, slippery word that anchors this entire story: abrupt. In everyday language, abrupt might mean a few days or a few weeks. Something sudden, something you notice right away. But in paleoclimate science, abrupt means something different, and honestly, something a little unsettling once you sit with it. When climate scientists say the 8.2K event was abrupt, they're usually talking about changes that unfolded over a decade or two, maybe a single human generation, sometimes possibly even faster. That might not sound instant by the standard of a news headline, but by the standard of ice cores and sediment layers, by the standard of processes that normally take centuries or millennia to unfold, a shift over 10 or 20 years is essentially a cliff edge. It's the climate equivalent of slamming on the brakes. And here's the part that should really sit with you. A shift like that isn't abstract to the people living through it. It's not a line on a graph. It's a grandmother who remembers the good years and a grandchild who's never known anything but hardship, both alive at the same time, both trying to make sense of a world that seems to be breaking the promises it made to their parents and their parents before them. 20 years is nothing to a glacier. It's everything to a farmer. So as we head toward the moment the shock actually arrives, the question worth carrying with you is this. Every society, ancient or modern, has some capacity to absorb change. A bad harvest here, a dry season there, a colder winter than expected. Communities build in buffers, stored grain, social networks, movement, flexibility, all designed to soak up the normal unpredictability of the world. But every buffer has a limit. At some point, if the change is big enough, or fast enough, or lasts long enough, the buffer fails, and the system underneath it has to bend or break. That's the real question sitting underneath everything we're about to explore tonight. Not simply what happened 8,200 years ago, but how much stress a still young experiment in farming and settlement and shared community life could actually take before something had to give. The early Holocene had given humanity a rare gift, a stretch of calm long enough to build something new. The 8.2K event was about to ask whether that something new could survive its first real test. To see that test coming, we have to step out of the villages and fields for a moment and into a place no human had ever walked 8,200 years ago. The interior of the Greenland ice sheet. If you could slice down through that ice, all the way from the surface to the bedrock, what you'd have in front of you would look almost like the cross-section of a tree. Layer upon layer, band upon band, each one a winter snowfall pressed and compacted by the weight of everything that fell on top of it afterward. The deeper you go, the older the ice. At the very bottom, you're looking at snow that fell when mammoths still walked and humans were just beginning to figure out what a spear thrower could do. Those layers are how we know what happened to the climate, and how fast. When snow falls, it doesn't all look the same at the atomic level. A tiny fraction of the water molecules are a little heavier or a little lighter, because they contain different versions of hydrogen and oxygen. Scientists call these versions isotopes. And here's the key. Warm air tends to carry and drop a different mix of those isotopes than cold air does. So the snow that fell on Greenland in a warm year is chemically distinguishable from the snow that fell in a cold year. Over time, as the snow turns to firn and then to solid ice, those isotope ratios are locked in place. Drill down through them with a long, hollow coring tube, pull up a cylinder of ice, and you're literally holding frozen air and water from a particular moment in the past. Measure the ratio of heavy to light oxygen or heavy to light hydrogen, and you get a remarkably precise thermometer for ancient Greenland. When scientists plot those isotope values against depth, a pattern emerges. Wiggles, spikes, plateaus, warm periods, cold snaps, brief stutters, long trends. Somewhere in that long undulating line, there's a sharp, narrow dip that wasn't there before the Holocene began. Cooler conditions, arriving quickly, then slowly easing back. Once the layers are dated and converted from meters below the surface into years before present, that dip lines up at roughly 8,200 years ago. That's where the name comes from. The 8.2K event is literally shorthand for a climatic anomaly centered around 8.2 thousand years before present, with present conventionally defined by geochemists as the year 1950. It's not the only wiggle in the ice. There are other cold blips and regional quirks scattered through the Holocene. But this one is global enough, sharp enough, and large enough to stand out from the background noise. In the Greenland cores, it's hard to miss. The isotope values drop like a step down in a staircase. Depending on which core you look at and how you process the data, you're seeing something on the order of a 3 to 6 degrees Celsius cooling in Greenland air temperatures, unfolding over a decade or two, lingering for maybe a century or two, then slowly relaxing back toward the previous baseline. Now, you might imagine those ice layers as perfect annual rings, one year neatly stacked on top of another like pages in a book. And in a way that's true up to a point. Near the top of the ice sheet, you can see distinct seasonal differences. Winter snow and summer snow compact differently, carry different chemical signals, even look slightly different under a microscope. That gives you what scientists call annual resolution. You can, in some segments, literally count years like you'd count the growth rings of a tree. Deeper down, though the story gets fuzzier, the weight of all that overlying ice squeezes the layers thinner and thinner. What started as a crisp division between one year and the next blurs out. Diffusion moves some of the isotope signal between adjacent layers. Eventually, the climate record becomes smoothed, averaged over several years, sometimes decades. You still see the big swings, but you lose some of the fine detail. For the 82K event that matters, in the upper parts of the Greenland cores that cover this time period, the resolution is still good enough to see how fast the cooling started and how long it lasted, but not always good enough to pin it down to the exact year. Was it 5 years from normal to cold, 10, 20? The ice alone can't always tell us. It shows us a cliff, but the exact angle of the drop is a little hazy. To sharpen the picture, scientists don't just rely on one core or even one type of archive. They look for the same fingerprint in very different places. In caves, for instance, water dripping from the ceiling slowly builds up delicate stone formations over thousands of years. Stalagmites, stalactites, thin flowstones. As that water evaporates and leaves minerals behind, it also leaves a record of its own isotopic composition and trace elements. Those cave deposits called speleothems can be dated very precisely using uranium-thorium methods. In some regions, they show a distinct shift around the same time as the Greenland signal. A change in the isotopes of oxygen that points to cooler conditions, altered rainfall patterns, or both. On lake bottoms, layers of mud quietly settle season after season. In some lakes, you get finely banded sediments with light and dark couplets that correspond to individual years called varves. In others, the layers are thicker, smeared across multiple seasons. But either way, those sediments trap pollen grains, fossilized algae, and tiny fragments of whatever was washing in from the surrounding landscape. Shifts in the kinds of pollen, in the types of algae, in the chemistry of the mud itself, line up in many places with the 8-2K timing. Trees retreating, grasses advancing, or simply evidence of drier, cooler conditions. Far from Greenland, out in the ocean, cores of seafloor mud carry their own story. Tiny marine organisms build shells out of the water they live in, and the isotopic composition of those shells reflects the temperature and salinity of the surface ocean. Layer by layer, those shells rain down, accumulate, and can later be sampled just like ice, only with sand and clay instead of snow. In parts of the North Atlantic, those marine records show a cooling surface, or changes in circulation, in that same narrow window centered near 8.2 thousand years ago. When you step back and overlay all these lines of evidence, the pattern is there. A coordinated, though not perfectly identical, cooling event affecting large parts of the northern hemisphere with ripple effects elsewhere. That's why most researchers accept the 82K event as real, not just a quirky local chill over Greenland. But the agreement isn't perfect, and the imperfections are where the uncertainties live. Different archives use different clocks. Ice cores have layer counting and volcanic markers. Caves and corals have radiometric dates. Lakes and peats often rely on radiocarbon. Each of those methods has its own blur, its own plus or minus. When you say something happened 8,200 years ago in an ice core and 8,200 years ago in a stalagmite, what you really mean is that each one happened sometime within a small window and those windows overlap. Sometimes they overlap neatly, Sometimes they're a little offset. On top of that, climate doesn't move in lockstep across the globe. A sharp, cold snap in Greenland might show up as a modest drying in the eastern Mediterranean, a shift in monsoon timing in India, and almost nothing detectable in a distant corner of the Pacific. The 8.2K signal is strong in some records, faint in others, and nearly invisible in a few places. That doesn't mean it wasn't global. It means that different regions and different systems respond in their own ways, with their own lags and thresholds. And finally, every proxy is a translation. The isotopes in ice are translating temperature and snowfall patterns into numbers. The chemistry of stalagmites is translating rainfall and cave ventilation into slow-growing stone. Pollen in lake mud translates plant communities into microscopic grains. None of these translations is one-to-one. They're all noisy, and they all come with assumptions. When a graph shows a neat, sharp line, there's a long chain of careful but imperfect interpretation behind it. So when we talk about the 8.2K event, we're really talking about a pattern that appears with slightly different accents in multiple independent records. A brief interruption in early Holocene calm, centered around 8,200 years ago, most clearly visible in the North Atlantic and surrounding regions. A cooling that unfolded fast enough to count as abrupt in the language of glaciers, and long enough to matter to farmers. With that in mind, we can finally turn from the layers of ice and mud back to the water that set the whole chain of events in motion. Because the leading idea about what triggered this sudden chill starts not in Greenland's sky, but in the enormous lakes left behind by the melting ice age. At the end of the last ice age, North America didn't look like the map you know. Across what is now Canada and the northern United States, a wall of ice still lingered. The Laurentide ice sheet. At its peak it had been more than 2 kilometers thick in places, a continent-sized cap of frozen water stretching from the Arctic almost to the modern Great Lakes, and from the Atlantic coast well into the interior. By 8,200 years ago, that sheet was a shadow of its former self, but it wasn't gone. Vast lobes of ice still covered parts of Hudson Bay and central Canada, and where that ice had once pressed the land down, huge basins had formed. When the climate warmed and the ice began to melt back, those basins filled. Imagine fresh water on a continental scale, not lakes like we know them today, but inland seas. One of the largest was what geologists call Lake Agassiz Ojibwe. It sprawled across what is now Manitoba, Ontario, and parts of the northern United States. Its surface area at times rivaled the Black Sea or the Mediterranean. Standing on its shore, if you were a hunter living in that landscape, you might have seen nothing but water all the way to the horizon, with ice still gleaming in the distance. For thousands of years, as the ice sheet retreated, the ways this enormous lake drained kept changing. Sometimes it spilled south toward the Mississippi Basin. Sometimes it found routes east or west. The details shifted as ice dams formed and failed, as the land itself slowly rebounded from the weight of the vanished ice. By the early Holocene, the system had reached a precarious balance. A giant lake, pinned against the shrinking edge of an ice sheet, held in place in part by walls of ice and in part by low ridges of land. Behind those walls, meltwater kept collecting. Rivers fed in. Glaciers dripped and cracked. Year after year the volume rose. The leading idea for the 8.2K event is that this balance snapped. At some point, between roughly 8,400 and 8,000 years ago, the final configuration of Lake Agassiz Ojibwe catastrophically changed. An ice dam failed, or a low divide was overtopped. Instead of draining gradually along old familiar routes, an enormous pulse of fresh water was suddenly rerouted toward the North Atlantic. The details of that routing are still being pieced together. One widely discussed pathway sends the water north, through what is now Hudson Bay, then outward into the Labrador Sea and subpolar North Atlantic. Another emphasizes more complex, shifting combinations of northern and eastern outlets. It's possible the drainage didn't happen in a single instant, like a bathtub plug pulled all at once, but through a series of pulses, surges and state changes spread over a few decades. What most researchers agree on is not the exact plumbing, but the outcome. A great deal of very fresh, relatively cold water ended up in the parts of the North Atlantic where the ocean normally breathes. Under modern conditions, the surface waters of the North Atlantic are salty and dense enough that in certain regions they cool, sink, and help drive a global conveyor belt of currents. That sinking is one of the engines of what climatologists call the Atlantic Meridional Overturning Circulation. You don't have to remember the name. The important part is that this overturning moves heat around the planet. It takes warm surface water northward, gives some of that warmth to the atmosphere, and returns colder, deeper water south again. Now picture what happens if you suddenly pour a lake's worth of fresh water into the area where that sinking usually happens. Fresh water is less dense than salty water. Mix enough of it into the surface ocean, and you make it harder for that water to sink. It's like pouring a layer of lighter fluid on top of something heavier. The more you dilute the salt, the more you weaken the engine. This is the crux of the trigger hypothesis. A relatively short-lived flood from the remnants of the Laurentide ice sheet into the North Atlantic perturbed the density structure of the surface ocean just enough, and just long enough, to slow down the Atlantic overturning circulation. How big was the flood? That's where the debates sharpen. Some reconstructions envision a truly enormous outburst, with water volumes in the range of many meters of equivalent global sea level rise, released over a century or less. Others argue for smaller, more prolonged discharges, or for a complicated combination, perhaps a major catastrophic release riding on top of an already elevated background of meltwater. Landforms around Hudson Bay and in the Great Lakes region show abandoned shorelines, spillways, and erosional scars that fit with a large outflow event. Marine cores off eastern Canada and in the subpolar North Atlantic preserve layers of lighter, fresher water signatures and changes in tiny fossil shells that hint at altered salinity and temperature during the right time window. But translating those traces into an exact gallons per minute number is difficult, and probably always will be. There's also uncertainty about just how fast the water hit the ocean. A single season? A few years? A human lifetime? The ice cores and sediment records we have smooth time together. What looks like a spike in the mud might be an entire generation's worth of floods blurred into one layer. Yet even with those uncertainties, the broad picture is consistent. A large pulse of fresh water reached the North Atlantic over a relatively short interval on the order of decades. The climate response, visible in Greenland ice and in many other records, lasted far longer on the order of centuries. That mismatch in timescales is important. The flood itself was brief in geological terms, and probably brief in human terms as well. The climate's response was drawn out, because it wasn't just reacting to the presence of the extra water. It was reacting to the way that water nudged the ocean circulation into a different mode, then slowly relaxed back. Once you weaken a system like the Atlantic overturning, it doesn't necessarily snap back the moment the perturbation ends. The density structure of the ocean has to rebuild. Salinity patterns have to re-establish, sea ice distributions adjust. Heat stored in the deep ocean and atmosphere finds a new balance. All of that has inertia, so in this view, the 8.2K event isn't really about a single dramatic flood on its own. It's about what happens when that flood arrives in exactly the wrong place, at exactly the right moment to interfere with one of the planet's major heat transport engines. a short, sharp jolt of fresh water delivered to the North Atlantic breathing zone, can translate into centuries of colder, drier, or simply different weather for people living thousands of kilometers away. To see how that translation works, we have to follow the water from the surface of the North Atlantic down into the depths, and watch what happens when the great overturning circulation takes a sudden, reluctant breath. To follow that reluctant breath, it helps to picture the ocean engine in the simplest possible way. Imagine you're standing on a beach somewhere in the tropics, maybe off West Africa. The surface water at your feet is warm, sunlit, and relatively light. Now trace that water, not with your eyes, but with your imagination, as it joins one of the great currents that slides along the ocean's surface. Some of that water will eventually be drawn northward as part of the Atlantic conveyor. It will drift, swirl, and be steered by winds, but on average it moves toward higher latitudes. As it travels, it stays salty. In some regions, it even gets saltier, as evaporation takes pure water away and leaves the salt behind. That salinity is important. It's like weight added to a suitcase. The more you pack in, the heavier it gets. By the time that water reaches the subpolar North Atlantic, near places like the Labrador Sea and the seas around Greenland and Iceland, it has two key properties. It's salty, and it's about to get cold. In winter, fierce winds strip heat from the surface. Sea ice forms and rejects some of its salt into the underlying water. Cooling makes the water denser. Added salt makes it denser still. Dense enough in certain favoured regions to begin to sink. This is deep water formation. It's one of the beating hearts of the Atlantic Meridional Overturning Circulation. Surface water cools and sinks, sliding down into the interior, then spreading southward at depth. To replace what has sunk, more warm water is drawn north at the surface. The system feeds itself. Sinking in the north pulls warmth from the tropics like a conveyor belt, delivering extra heat to the atmosphere over the North Atlantic and Western Eurasia. That's why climatologists are so focused on this circulation. It's not just a local curiosity, it's a major way the planet moves heat around. Now take that simple picture and add the flood. You have surface waters in the North Atlantic that normally become cold and dense enough to dive. You suddenly dilute them with a huge volume of fresh meltwater. Same temperature, less salt, less dense, harder to sink. You don't have to shut the engine off entirely to make a difference. You only have to slow it. Models and reconstructions of the 82K event suggest something like this. As the meltwater pulse reached the North Atlantic, deep water formation in key regions weakened. The overturning circulation slackened. With less dense water sinking, less warm water was pulled northward at the surface. The North Atlantic lost some of its heat supply. One way to think about it is to imagine a house heated by radiators. The boiler is still running, but you partially close the valves to the upstairs rooms. Downstairs might stay fairly warm, upstairs cools. That's the sort of pattern expected from an AMOC slowdown, not an instant global ice age, but a rearrangement of where the heat goes. The immediate fingerprint shows up close to the action. Ice cores from Greenland record a sharp temperature drop of several degrees. Marine sediments from the subpolar North Atlantic show signs of cooler surface waters and more extensive sea ice. Some records suggest winters became especially severe in regions downstream of the North Atlantic storm track. Those storm tracks themselves likely shifted. Over the Atlantic, mid-latitude weather systems follow preferred paths, guided by contrast between warm and cold air masses and by the position of the jet stream. When you cool the North Atlantic relative to lower latitudes, you alter those contrasts. In many simulations of an 82K style meltwater pulse, the belt of storms nudges southward. Regions that had been beneath frequent, moisture-laden, low-pressure systems can find themselves on the quieter, drier side of things. Other regions see more storms than before. That's one reason the 82K event doesn't show up as a uniform signal everywhere. The world didn't simply get colder. Some places cooled dramatically. Others cooled modestly. Some saw their rainfall decrease. Others saw it increase or become more seasonal. The AMOC slowdown acted less like a universal dimmer switch and more like someone rearranging the light fixtures in a very large, very complicated room. Globally, the energy balance of the planet didn't suddenly change because of this one flood. The sun kept shining with the same intensity. Greenhouse gas levels in the atmosphere didn't crash. What changed was the routing of that energy. Less heat transported north by the Atlantic meant more heat retained elsewhere, in other ocean basins, in the tropics, and in the southern hemisphere. The climate system responded by shifting winds, storms, and rain belts to find a new, temporary balance. That's why the North Atlantic is so central in this story. It's not the only ocean region that matters, but it's one of the primary places where surface waters decide to sink, disturb that choice, even for a few decades, and the consequences ripple outward along the whole overturning pathway, from Greenland to the British Isles, from the eastern seaboard of North America to the Mediterranean, from the African monsoon belt to the South Atlantic. At the same time, researchers have suggested that the 82K event may not have been driven by AMOC changes alone. Some point to gradual background shifts already underway, the lingering adjustment of ice sheets and sea level after the last glacial maximum, slow changes in Earth's orbit and seasonal sunlight, volcanic activity that may have added its own shorter-term pulses of cooling. Others argue for internal climate variability, natural swings in ocean atmosphere patterns that could have amplified or dampened the effects of the meltwater pulse. In this view, the Laurentide flood was a key nudge applied to a system that was already wobbling in certain directions. The AMOC slowdown provided the framework: cooler North Atlantic, altered storm tracks, repatterned rainfall. Other processes filled in the details, shaping exactly which regions tipped into crisis, which merely felt a chilly breeze, and which might have seen opportunities in newly emerging climates. For the people living through it, none of these mechanisms had names. They would never see the Atlantic, much less diagram its overturning cells. What they knew was simpler and far more immediate. Winters that bit harder, summers that came late or failed, rains that shifted on the calendar or did not arrive at all. From the slow breath of the deep ocean to the anxious glance at a cloudless sky, the chain reaction was complete. In the next part of the story, we'll move from the engine room of the Atlantic back onto land and try to feel what this centuries-long anomaly actually meant, season by season, for the communities who had built their lives in what they thought was a newly stable world. For someone living in the early Holocene, the change would not have begun with a graph or a number. It would have begun with a feeling. Perhaps the first hint came in winter. In many regions influenced by the North Atlantic, winters had already been comparatively mild for a world so recently out of an ice age. Snow came and went. Rivers froze, but not always deeply. Livestock and wild game could often graze or forage through much of the cold season. Then, over the course of a few years to a few decades, that pattern began to shift. Snow settled earlier and stayed longer. Frost hardened the ground deeper. Lakes that once skimmed with ice now locked up solid. The familiar shoulder seasons, those messy, slushy weeks of in-between, began to narrow. In some places they almost snapped shut. Autumn tipped faster into real cold. Spring took its time coming back. Paleoclimate records from Greenland suggest temperature drops on the order of 3 to 6 degrees Celsius at the peak of the 82K event in the high north. On paper, that sounds modest compared to an ice age. In daily life, it could mean the difference between a river that thaws in late March and one that doesn't break up until May. between a soil that is workable in time for sowing and one that remains cold and stubborn while the planting window quietly closes. For early farmers, that mattered more than any average. Imagine you're part of a community in the Near East, already experimenting with barley, wheat, lentils. Your parents and grandparents have built a calendar not by numbers on a page, but by the flowering of certain plants, the calls of birds, the level of water in a nearby stream. For a couple of centuries, that calendar has been reasonably trustworthy. Then, during your lifetime, it starts to slip. You plant when your elders say it's time, but the soil is still chilled. Seeds rot or sprout weakly. A late cold snap clips tender shoots. A season that was once good enough now straddles a new threshold and falls on the wrong side of it. The key point here is that the global cooling signal associated with the 8.2K event was, in many places, relatively small when averaged over the year. But climate is felt locally through extremes and timing, not through averages. A drop of 1 or 2 degrees in mean summer temperature might not sound catastrophic, yet it can shorten the frost-free season by several weeks. It can shift the probability of a killing frost from every decade to every other year. Small shifts in the baseline load the dice. This loading did not involve temperature alone. Water moved too, sometimes away from where people most needed it. As the North Atlantic cooled and storm tracks shifted, precipitation patterns reorganized. In some middle latitude regions, rainfall totals declined. The same cooling that intensified winters could, in summer, mean weaker onshore winds, fewer moist air masses penetrating inland, more clear, dry days stacking up behind one another. In the circum-Mediterranean and parts of the Near East, multiple lines of evidence hint at drier conditions during and after the 8.20K event. Lakes dropped, river discharge diminished, cave formations, stalagmites slowly built by dripping water, record intervals of reduced drip rates or changes in the isotopic composition of the water, consistent with less rainfall or altered seasonality. Elsewhere, the story was more complicated. Some regions may have seen an increase in rainfall but packed into shorter, more intense wet seasons. That kind of shift can be as disruptive as outright drying, heavier storms that erode fields, wash away seeds, and then leave longer dry gaps before the next rain. This is where the idea of teleconnections comes in. The Meltwater pulse and AMOC slowdown were physically centered in the North Atlantic, but their influence did not stop at the coastline. Changes in sea surface temperature and sea ice cover altered the position of the jet stream and the main storm tracks. Those in turn nudged the great tropical rain belts, the intertropical convergence zone, monsoon systems, by small but consequential distances. Monsoon rains over West Africa, for example, are partly tied to how warm the North Atlantic is relative to the Southern Hemisphere. Cool the Northern Ocean, and the whole atmospheric circulation can tilt, drawing the zone of strongest rainfall slightly southward. That means fewer dependable summer rains at the northern margin of the monsoon, where communities are most exposed to failure. Farther afield in South or East Asia, teleconnections work through a chain of cause and effect. Altered North Atlantic temperatures change the planetary wave patterns in the atmosphere. Those waves reshape high-altitude wind fields, and those winds influence how strongly and when monsoon systems develop each year. The result is that a freshwater flood thousands of kilometers away can subtly adjust the odds of a strong or weak monsoon, an early onset or a delayed one. Again, the key word is subtle. We are talking about nudges, slightly cooler seas, slightly shifted pressure patterns acting on systems that are already variable. But for societies that had tuned their agriculture and seasonal movements to the Holocene's comparatively stable baseline, those nudges mattered. One way to sense this is to think about risk rather than means. Before the 82K event, in many regions, maybe 1 year in 10 was truly bad, severe drought, failed harvests, desperate measures. The rest might range from poor to excellent, but outright catastrophe was rare enough that communities could bounce back. Under the altered pattern, the truly bad years may have become 1 in 5, or 1 in 3. Not everywhere, not all at once, but along certain climatic margins. You could still have good years, the sky could still open with generous rain, but the clustering of failures changed. 2 or 3 weak harvests might arrive back to back, with no recovery interval. Livestock herds could be run down, seed grain eaten, social promises broken under the weight of necessity. The timescale of the event helps explain how this played out in human terms. Ice cores suggest a relatively sharp onset, perhaps over the course of a few decades into the coldest phase, followed by a more gradual recovery over 1 to 2 centuries, with regional aftershocks that may have persisted even longer. For individuals, that means you might remember your grandparents speaking of the old winters as milder, the rains as more regular. By your own middle age you might see some easing. But for your children and grandchildren, the anomaly wasn't an event. It was simply the way the world was, and because the signal was uneven, some valleys, coasts and river corridors became comparative refuges, where cooling and drying were muted or even beneficial. Others slipped past invisible thresholds, turning once viable fields into marginal gambles. In the next parts of this story, we'll walk through some of those regions, starting in the Near East, and see how harsher winters, fickle rains, and shifting seasons translated into choices to move, to store, to bargain, and to reimagine what it meant to live at the edge of predictability. If we zoom in now on the Near East, the story sharpens. The early Holocene green of the Fertile Crescent is famous, but it wasn't uniform. Think of it less as a single lush strip, and more as a gradient, running from relatively reliable wet zones into places where farming was always a bet against the sky. On the western and northern flanks along parts of the Mediterranean coast, in the foothills of the Zagros and Taurus, annual rainfall could easily top 500 or 600 millimetres. In those lands, barley and wheat could often grow without help beyond digging, sowing and keeping animals off the fields. Farther south and east, though, rainfall tailed off. You pass through a band of maybe 200 to 300 millimetres a year, what climatologists would call semi-arid steppe, before you slip into true desert where rain is too rare and unreliable to sustain crops year after year. It's in that middle band, along the margins, that the 820K event really bites. Those steppe zones are rain-fed, but barely. A cereal like barley might tolerate poor conditions better than wheat, but it still needs enough moisture at the right time. If total rainfall drops a little, or shifts out of the sensitive stages of growth, you don't just get somewhat lower yields, you cross a threshold where entire fields can fail. Archaeologists studying sites in northern Syria, southeastern Anatolia, and the Jazeera Plain often emphasize this threshold quality. In good years, rain-fed fields could produce surpluses, support flocks of sheep and goats, and encourage the building of more permanent houses, storage pits, even small communal structures. In bad years, the same landscape could flip into a place where the soil cracked, springs shrank, and fresh pasture retreated into scattered patches. Layer an 8-2K style cooling and drying on top of that, and the gambling odds change. Cooler conditions can delay the start of the growing season. Seeds sit longer in cold ground before germinating, making them more vulnerable to rot, pests, or sudden dry spells. If spring rains are weaker or end earlier, crops may not develop enough before soil moisture is spent. Stressed plants produce fewer seeds, poorer straw for fodder, and are more likely to be wiped out by one ill-timed frost. For herders, the picture is no easier. Sheep and goats can handle patchy resources better than cereals, but they still need water and enough vegetation to keep body weight up, especially through winter and around lambing. If winter snows linger longer in uplands and summer drought deepens in lowlands, the seasonal routes that flocks once followed may no longer line up with green growth. Pastures that usually come through in a lean year might fail 2 or 3 years running. Under those conditions, the simple question facing many communities becomes, do we stay, do we move, or do we change what we do? Some scholars argue that during and after the 82K event, marginal rain-fed zones were partially abandoned. Settlement surveys in parts of northern Mesopotamia and the Syrian steppe show apparent dips in site numbers around this time. One interpretation is that people retreated toward more dependable water, river valleys, springs, and better watered uplands, concentrating population where the climate shock was cushioned. Others see a more complex pattern. Instead of straightforward abandonment, there may have been a shift in emphasis, less investment in fixed, heavy architecture on the margins, more reliance on mobile herding, seasonal camps, and flexible use of multiple ecological zones. In this view, people didn't simply leave the drylands, they learned to treat them as part of a larger mobile strategy. Still others caution against tying every settlement fluctuation directly to climate. Political alliances, trade routes, soil exhaustion, even outbreaks of disease could also nudge communities to reorganize. The 820K event might be one factor among many, amplifying existing stresses rather than dictating a single clear response. Whatever the mix of causes, the underlying choices had a similar flavor: reduce risk, spread exposure, and buy time. One obvious tool was storage. Earlier Neolithic communities in the Near East already used storage pits, silos, and large jars. Under more erratic rainfall, the importance of these structures almost certainly grew. A surplus from one good year could be turned into insurance against one, or even 2, bad ones. But storage itself changes social relations. Somebody has to control the granary, decide when to open it, and arbitrate who gets how much. In some scenarios, this encourages cooperation and risk sharing. Households might pool grain, or clans might maintain communal reserves that are ceremonially opened in times of need, reinforcing bonds of reciprocity. In other scenarios, control over stored food becomes a source of power, letting certain lineages or individuals leverage scarcity into influence. Mobility was another lever. Flock owners could expand their grazing loops, pushing farther into steppe during the brief windows when it greened, then falling back to riverine or upland refuges when it dried. Farmers could experiment with mixed strategies. Some fields near the home settlement, some planted in outlying patches accessed seasonally, some relatives or allies maintaining gardens in wetter microenvironments. Risk could also be shared horizontally through networks, exchanging marriage partners, gifts or livestock between distant communities meant that a run of bad years in one locality did not automatically translate into total collapse. You could in principle call in favours, send young animals to relatives in better watered zones, or migrate temporarily to in-law territory. Within the scholarly literature, you'll find versions of this period painted in different shades. One picture emphasizes stress and contraction. Cooler, drier conditions push farmers off the margins, reduce yields, and trigger a retreat to environmental refuge. Another stresses innovation and diversification. Communities respond by combining crops and herds in new ways, by extending mobility and trade, by spreading their bets rather than stacking everything on one patch of rain-fed barley. A third perspective suggests that for many people, the changes may have been gradual enough and mixed enough that they adapted without dramatic breaks. By quietly adjusting planting dates, adopting slightly more drought-tolerant varieties, or renegotiating grazing rights with neighbours, In all of these, climate does not act as a single irresistible force. It sets the background probabilities, the frequency of good years and bad. Human societies, even in the early Holocene, make choices within that altered landscape of risk. Those choices, how much to store, how far to move, how widely to weave networks of obligation, begin to create new patterns on the map. And in the Near East, one of the most consequential patterns to emerge from this era of unstable rain would be an ancient decision to stop waiting quite so patiently for the sky and to start coaxing water into new paths of its own. When people stop waiting for the sky and start moving water with their own hands, the landscape itself becomes negotiable. In parts of the Near East, that negotiation was possible in a very literal way, because the land came with something like a built-in safety net, rivers that did not care quite as much about one bad rainy season. The Tigris and Euphrates, for example, drain huge catchments. Snow in distant mountains, storms hundreds of kilometers away, slow groundwater contributions, these all feed into the same channels. Even if local rain falters, the main river may still swell with water from somewhere else. It's not that rivers are immune to climate shifts, but they integrate weather over space and time. They smooth out some of the noise. To a community living on the edge of rain-fed failure, that smoothing matters. If your fields are on a high step where everything depends on a few months of decent rain, an 8-2K style event can flip you from usually okay to often not. But if you're close to a major river, or a spring, or a reliable stream fed from upland snow, you have another knob to turn besides hope and storage. You can try to move the water. The earliest efforts were probably simple. Diverting a bit of floodwater onto an adjacent patch of soil, scraping a shallow channel from a spring to a garden, blocking a small gully with brush and earth so that runoff spreads out and soaks in instead of tearing past. Things that could be done with a few people and some days of labour. Some archaeologists argue that it's under periods of heightened climatic stress, events like 8-2K, that these modest tricks become more tempting and more necessary. When the odds shift against you, the payoff for any small improvement in water control goes up. In this view, marginal communities edging back toward rivers in the wake of poor years might not just be retreating, they might also be experimenting, trying slightly deeper channels, broader diversions, more organised schedules for who can take water when. Maybe one household digs a furrow to catch overbank flow, another lines a ditch with stones to keep it from collapsing, a third figures out that a shared embankment could protect everyone's plots from an especially aggressive flood. Over generations, a scatter of experiments can coalesce into something more recognisable as irrigation. Long before the monumental canals of later Mesopotamian kingdoms, there were likely patchworks of small-scale works, feeder ditches, weirs, temporary levees, seasonal basins that trapped silt and moisture. They might not look like much from a modern aerial view, but in a world of unstable rain, each one is an attempt to trade uncertainty in the sky for something firmer on the ground. Of course, that trade comes with a price. Water is not like wild pasture that anyone's flock can wander across. Once you've carved channels into the earth, someone has to maintain them. Silt builds up, banks erode, storms punch holes in carefully shaped walls. If you leave a canal alone for even a single season, nature starts taking it back. So the more you rely on managed water, the more you tie yourself to regular collective labour. Irrigation historians often emphasise this. A canal is not just a trench, it is a schedule. People have to agree on when to clear it, who brings tools, whose stretch gets fixed first. They need some way to handle conflict when one farmer claims his neighbour is stealing too much water or blocking the flow at the wrong time. Even small disputes can matter if the whole harvest is riding on the timing of a few crucial days. Out of those practical needs can grow new forms of coordination and new opportunities for inequality. In one scenario, communities solve the problem through fairly horizontal means. Elders arbitrate disputes. Work parties are organised on a rotating basis. Access to water is tied to membership in the community rather than to personal status. These are arrangements many anthropologists see in smaller-scale irrigation systems around the world. In another scenario, someone steps forward or is allowed to step up to manage things more regularly. The person who can read the river, who knows when the flood is coming, who can mobilize enough hands to repair a breach quickly, may gain prestige. They might begin to be the one who says when the gate opens, whose fields get flooded first, whose debts can be repaid in labour on the canals. When climate instability increases dependence on managed water, control over that water becomes a lever. Not necessarily a lever for despotic kings, that is a later story, and a contested one, but a lever all the same. The infrastructure that buffers you against bad years can also become the infrastructure through which power is exercised. Here, it helps to contrast the lowlands with those rain-fed uplands we just left. In the steppe and foothills, risk can be managed by moving, shifting flocks, spreading fields, deepening storage, leaning harder on exchange networks. Your vulnerability is to the sky, but your flexibility is geographic. If the rains shift, you can, to some extent, shift with them. In the river valleys, especially as irrigation tightens its grip, flexibility looks different. You may be better buffered against a run of drought years, but only if the canals are intact, the embankments hold, and the agreements over water rights do not break down. You trade a direct dependence on rainfall for a dependence on infrastructure and the social agreements that keep it running. This doesn't mean the 82K event caused irrigation in any simple sense. People had been experimenting with water in the Near East for a long time by then. In some regions, small-scale irrigation may have begun even before the cooling pulse. In others, it may not have taken off until centuries after. Climate in this story is less a switch and more a background hum that gets louder. As the reliability of rainfall becomes more questionable in certain zones, the relative attractiveness of water management rises. Communities that were already dabbling in diversion works might invest more. Those on the margins might relocate toward valley bottoms where the rivers offer a different kind of stability. Local politics, soil conditions, traditions of cooperation or rivalry, all of these mesh with the climatic signal to shape what actually happens. What we can say is that by the time the dust of the 82K event settles, parts of the Near East are beginning to look different on a map of human control. Lines of water no longer follow only gravity. They start to trace the choices and compromises of villagers. The landscape is being rewired, not just by colder winters and shorter rainy seasons, but by ditches, bunds, shared embankments, and the social knots tied around them. This quiet reworking of water sets up many of the contrasts that will deepen in later millennia, between valley and steppe, between households tied to fixed plots and those who keep their options open, between those who can walk away from a bad year and those whose survival is literally channeled between built banks. And beyond the Near East, similar questions are beginning to surface wherever rivers, lakes and deltas offer the tempting possibility of smoothing out a rougher climate, if people are willing to accept the new kinds of dependence that come with it. If the Near Eastern river valleys were beginning to knot themselves around water, the lands to the northwest were feeling the same climatic pulse in a different way. Anatolia and southeast Europe at the time of the 82K event were not empty frontiers. They were the middle stretches of a great experiment in farming on the move. From the Levant into central Anatolia, across the Aegean, up the Danube and along the Balkan coasts, you can trace what archaeologists sometimes call Neolithic corridors, pathways along which crops, animals and ways of life spread. not as a single wave, smooth and even, but as a patchy advance. A village here, a cluster of sites there, with stretches of forest, steppe and mountain in between. These routes weren't arbitrary. They followed things that mattered to early farmers, soils that could be turned by simple tools, rainfall that usually arrived when needed, passes that let people move herds and seed grain without heroic effort, valleys that linked coast to interior like beads on a string. Now imagine that string under tension. A cooling of a degree or two, a shortening of growing seasons, a few unlucky years where spring rains fail or arrive at the wrong time, in a marginal patch. That's enough to turn a promising stop on the route into a dead end. The corridor doesn't vanish, but its shape changes. One valley becomes unreliable. Another, with a slightly different slope or exposure, suddenly makes more sense. This is where the archaeology gets very quiet and very suggestive. In parts of central and western Anatolia, some tell sites, those layered village mounds that build up when people live in the same place for centuries, show interruptions in their sequence. A layer of dense occupation, then a thinner band with fewer traces, sometimes even a gap where it seems nobody was living there for a while. In southeast Europe, along some branches of the Danube and its tributaries, early Neolithic settlements appear, flourish briefly, and then are followed by zones where we see fewer or no sites for a stretch of time. Archaeologists call these patterns hiatuses, a break in continuous use. On paper they look like pauses, on the ground. They may have felt like a generation deciding not to rebuild or to move down slope or to try their luck in the next valley over. But hiatus is only one kind of sign. In other places, instead of disappearance, we see reorganization. House plans change. The orientation of a village shifts. Storage features multiply or move from public to more private spaces. In some Anatolian sites, animal bones in rubbish pits show a subtle increase in herding relative to hunting, or a change in which domestic species dominate. In Balkan settlements, the proportions of wild resources, nuts, game, gathered plants, in the diet sometimes tick upward after a period of stress. Taken together, these are the kinds of clues people look at when they ask whether something like the 82K event left a footprint. They don't shout climate disaster. They whisper about adjustment. A useful way to think about this landscape is not as one big climatic region, but as a patchwork of microclimates. A north-facing slope that holds frost longer, a south-facing ridge that warms early in spring, a valley bottom with cold air pooling at night, a limestone plateau that drains too fast, a clay-rich basin that holds water even in a dry year. When a cooling pulse moves through such a patchwork, it doesn't hit everything equally. Some pockets may slip just past a threshold. Barley that used to ripen now fails 1 year in 3. Other pockets barely notice, buffered by local quirks in wind, soil and water. The result is a staggered impact. One community might experience a crisis and pull back or reorganize, while a group only a few days' walk away manages with little more than grumbling over a chilly spring. This staggered pattern may be part of why the spread of farming into southeast Europe looks, at times, like a series of starts and stalls. The broad trend is outward into new lands, but at finer scales we see retreats from certain uplands, increased density in more sheltered basins, or renewed emphasis on riverine zones where floods and groundwater soften the blow of drier years. How people absorbed these shocks depended a lot on their economic mix. Groups practicing mixed farming, cereals plus pulses with a few different herd animals, had more knobs to turn. If wheat struggled, barley might still make it. If fields near the village failed, a few more animals could be grazed further out, converting rough pasture into milk and meat. Herding flexibility becomes a kind of climate insurance. You can move sheep higher in a cool summer, tuck cattle into valley bottoms in a cold, dry winter, thin the herd when fodder runs short. Woodlands added another layer of resilience. Much of southeast Europe was forested or park-like at this time. Trees don't care as much about 1 or 2 bad years of rain as annual crops do. Nuts, fruits, browse for animals, firewood, construction timber, all of these can buffer households when fields perform poorly. Archaeological evidence for increasing use of woodland products after periods of settlement disruption suggests that people leaned into this safety net when they had to. So along these Neolithic corridors you can picture different strategies playing out. One village doubles down on cereals, digs more storage pits, tightens cooperation to get the harvest in during shorter, riskier windows. Another leans harder on herding, treating fields as a bonus rather than a guarantee. A third shifts its centre of gravity toward the forest edge, weaving more acorns, wild pigs, and gathered plants into daily life. From a distance of 8,000 years, this invites a tricky question. Were these regions collapsing under the weight of climate stress? Or were they reconfiguring, changing their spatial footprint, their diets, their social rhythms to fit a cooler, more capricious world? The temptation is always to draw a bold line. Here, a culture ends. Here, a route breaks. Here, a corridor closes. But when you look closely at Anatolia and Southeast Europe, around the time of the 82K event, what you see more often are bends than breaks, gaps in one valley paired with new sites in another, simpler house plans replacing more elaborate ones, diets tilting toward flexibility rather than specialization. It may be more accurate to say that the climate shock put the Neolithic roots under pressure, and under that pressure the roots kinked, braided, and sometimes thinned, but did not simply snap. The farmers and herders moving through these landscapes were not passive pieces on a climatic game board. They were constantly watching the sky, the soil, the health of their animals, the stories of neighbouring villages. They could redirect their movements along safer corridors, concentrate in microclimatic refuges, or experiment with new mixes of crops and flocks. In that sense, the tension between collapse and reconfiguration is less a verdict and more a spectrum. Some communities likely did fail and vanish from the record. Others bent, adapted, and emerged with slightly different lifeways, different routes, different dependencies. As the cooling pulse ebbed and the centuries rolled on, the map of early European farming would continue to thicken, but its shape had been subtly altered by those years of strain. The same corridors that had carried wheat and sheep now carried memories of bad springs, cautious settlement choices, and a deeper appreciation for the places where climate, topography, and human ingenuity could still line up in their favour. If Anatolia and the Balkans were the knot where new farming ways were tightening, Europe's north and west were more like the loose fringes of the tapestry. Here, the 82K cooling pulse met worlds that were not yet fully Neolithic, not fully Mesolithic, but something in between. Pioneering farmers edging into river valleys and long-established hunter-fisher-forager groups still rooted in coasts, estuaries and great forests. And again, the impact depended on where you stood. Along the Atlantic seaboard, from what is now Portugal up through Brittany, the Low Countries and the North Sea coasts, people had built lives around shores that were still adjusting after the Ice Age. Sea level was rising on the long timescale, reshaping bays and inlets, drowning old river mouths, and creating new estuaries rich in fish and shellfish. Then, a cold jolt like the 82K event arrives, and the ocean doesn't just get a little cooler. Storm tracks likely shift, winds stiffen and change their seasonal rhythm. Coastal productivity, the invisible web of plankton, fish, shellfish, seaweed, can flicker up in some places and down in others when temperature and mixing change. For communities whose year is organized around tides, fish runs, and seal migrations, those shifts bite. In some inlets, colder surface waters and stronger winter storms may have stirred nutrients more effectively, boosting certain fish populations. In others, harsher seas might have made small boat travel riskier for weeks or months at a time, cutting people off from favoured fishing grounds or from trading partners across the water. Archaeological layers in some shell middens, those long-used rubbish heaps of shells, bones, charcoal, show subtle changes around this time, different shellfish species dominating, a greater reliance on one kind of fish over another, occasional pulses of marine mammal bones. It's not a simple before and after line, but it hints that coasts were being renegotiated. Navigation too would have felt different. Shorter calm seasons, more frequent gales, sudden fogs or hard squalls tied to a cooler, more unstable atmosphere make even familiar waters unpredictable. For small craft that can shift where it's safe to cross a strait, when you risk an offshore island, or how often you dare to fish exposed banks, a route that felt straightforward for your grandparents might become a story of near misses in your generation. Inland, another transformation was underway. As the early Holocene warmed, Europe's Ice Age tundra and steppe had already been giving way to forests. Around the time of the 8-2K event, pollen records from lake sediments and peat bogs in regions like Britain, Ireland, northern France, and the Low Countries showed dense spreads of deciduous woodland, hazel, oak, elm, and in cooler or wetter spots, more conifer. The cooling pulse doesn't simply roll that change back. Trees are slow to respond, but the composition of forests seems to shuffle. In some cores, warmth-loving species pause, or even decline slightly. More cold-tolerant or moisture-loving trees creep upward in the pollen mix. Peat records suggest local increases in humidity in some bogs, while others point to brief drying phases. Taken together, these small botanical and chemical shifts are how we know that temperature and moisture regimes were wobbling, even if the overall forest cover stayed high. For people moving through those woods, the details mattered. A hazel-rich woodland is like a supermarket for Mesolithic groups, nuts in abundance, undergrowth that shelters deer and boar, straight rods for tools and huts. If cooling alters flowering times, nut yields can become more erratic. If some slopes get cooler and wetter, undergrowth might thicken differently, shifting where game prefers to browse, where you can track quietly, and where movement becomes a struggle. For the earliest farmers nosing into these forest margins, the challenge was different again. Fields had to be carved out of trees, and in a climate where growing seasons could suddenly shorten, the line between viable clearing and waste of effort was thin. Lake cores from parts of northwestern Europe show slightly cooler surface waters and changes in plankton communities at this time, consistent with shorter warm periods. Peat chemistry hints at water tables rising in some basins, lowering in others. Those changes would have made certain valley bottoms boggier, some floodplains more prone to waterlogging, and some light soils drier than before. If you were trying to push a Near Eastern crop package, wheat, barley, pulses into this mosaic, a few cooler, wetter springs or badly timed frosts could make the difference between a successful plot and a clearing that never quite pays back the labour of tree felling. So how did people respond? One pattern that shows up again and again in the northern and western record is flexibility in movement. Rather than fixing themselves in one tight cluster of permanent villages, many groups seem to have maintained or even intensified seasonal mobility. In forested regions, small camps appear and vanish around lakes and rivers, suggesting rounds that followed fish spawning, waterfowl migrations, nut harvests and game movements, where early farmers were present on the better soils. There's evidence that some communities combined small plots with seasonal hunting and foraging elsewhere. A field near the river, a summer camp at the forest edge, autumn trips to known nut groves. broader diets seem to have been part of the answer. Animal bone and plant remains from sites in northern France, the Low Countries, and southern Britain often show a mix that includes terrestrial game, freshwater fish, sometimes marine resources, wild plants, and where farming had arrived, modest amounts of domestic cereals and animals. Around the time of climatic stress, the relative contributions can shift toward diversity rather than specialization. More species represented, more habitats tapped. Toolkits quietly echo this. Microliths, tiny stone blades used in composite arrows and spears, remain important for hunting in forest and marsh. At the same time, edge-ground axes and adzes, suitable for felling trees and woodworking, become more common in some regions as forests thicken and the potential for clearing or constructing changes. On coasts and estuaries, fishing gear evolves. There are hints of changing fish capture strategies, different net weights, hooks and harpoon types that might track shifting species availability or new, more cautious ways of exploiting stormier waters. A slightly different angle on a bone harpoon or a new pattern of barbs can be read as a micro-adjustment to how fish behave in colder currents, or how seals haul out when ice and waves change. None of this unfolds evenly. Western Iberia, catching different ocean currents and wind patterns, may have experienced the cooling and moisture shifts differently than, say, the southern North Sea basin. Parts of Ireland and Scotland, already cool and wet, might have tipped further toward bog and heath, while sheltered lowlands in northern France barely crossed any ecological threshold at all. The result is not a single uniform, northern European response to the 812K event, but a patchwork, a checkerboard of coastlines where fishers recalibrated their rounds, forests where hunters retuned their seasonal circuits, and river valleys where, in a few favoured pockets, early fields took hold while others were abandoned or postponed. From a high altitude, the story can sound simple: a brief cooling, some extra storminess, forests still thickening across the continent. On the ground, it was lived as a series of local puzzles. Is this cove still worth launching boats from? Does this clearing give us enough grain before the frosts? Have the deer shifted to the north slope now that the south is too wet? Do we invest in heavier axes or more flexible hunting gear? In Europe's north and west around the time of the 82K event, people answered those questions not by transforming their worlds overnight, but by nudging the dials, moving camp a little differently through the year, widening what counted as food, tinkering with tools to match new patterns of forest, water and wind. While farmers to the southeast were feeling the pressure along their corridors, these coastal and woodland societies were quietly testing another kind of resilience, one that would matter immensely. As the Holocene climate kept shifting, and as new frontiers drew human attention further south, toward places where water itself was beginning to change its paths, further south, those changing paths of water led into a very different kind of experiment. At the time of the 82K event, the word Sahara wouldn't have meant what it does to us. Instead of a vast continuous desert, much of North Africa was in the middle of what scientists call the African humid period, a long phase when the summer monsoon pushed much farther north than today. Imagine bands of summer rain reaching deep into what is now hyper-arid sand and rock, lakes dotting depressions, seasonal rivers and marshes, grasslands and scattered trees spreading across areas that, in the modern world, barely see a cloud. For humans and animals, this wasn't a marginal wasteland. It was a mosaic of opportunity. Pastoral lifeways moving with herds of cattle, sheep, goats seemed to have been emerging around its wetter fringes. People camped by lakes that rose and fell with the rains, leaving behind pottery, stone tools, and layers of fish, bone and hippo remains that only make sense in a landscape of standing water and rich vegetation. Those lakes were more than scenic backdrops. In a seasonally dry land, they were anchors for entire systems, pastures radiating out where grass grew thick after the rains, migration routes that followed the filling and shrinking of basins, social meeting points where scattered groups could converge when water was abundant. All of this depended on a delicate atmospheric engine, the northward pull of tropical moisture each summer. When the northern hemisphere cools even slightly, that engine can slip a gear. One way to picture it is to think of the monsoon as a huge seasonal inhalation of air toward the hottest land. If high northern latitudes suddenly lose heat, as they likely did when fresh meltwater slowed the North Atlantic's overturning circulation, the contrast between equatorial warmth and northern cool changes. The zone where rising air and heavy rains spend their summer can shift a little south, or simply weaken. Climate models that simulate an 8-2K style cooling tend to show something like this. African monsoon rains pulling back, not vanishing, but failing to push as far into the continent as before. Less time each year when the northern Sahel and Sahara margins sit under thick, dependable rainy cloud, on the ground that doesn't translate into an instant desert. It means a series of small disappointments. Lakes that had been stable for generations might stop overflowing their outlets, then drop a meter, then 2. Shorelines creep inward. Papyrus beds thin, fish catches decline. The green belt around a basin narrows, forcing both animals and people into tighter circles around the remaining water. Geologists and paleoclimatologists read these changes in subtle traces. Lake cores from places like the Central Sahara and Sahel often show shifts in sediment, layers rich in organic material and fine mud during wetter phases, grading into coarser, wind-blown dust as conditions dry. Around the time of the 8-2K event, some records show brief drops in lake level, more carbonate crusts, or spikes in material that looks like it came in by wind rather than river. Marine cores off West Africa tell a parallel story. As the continent dries, more dust gets lofted into the atmosphere and carried out over the ocean. In some cores, layers dated near 8,200 years ago contain higher proportions of Saharan dust, hinting at a temporary strengthening of aridity and wind erosion on land. Inside caves, dripstones, stalagmites and stalactites quietly track rainfall chemistry. In North African and Arabian speleothems, shifts in oxygen isotopes and growth rates around this time are often interpreted as changes in moisture supply, though the exact meaning can be debated. Some show brief excursions consistent with drier conditions, others a more complex pattern, and the debates are real. Not every lake dries at the same moment. Not every dust core spikes in lockstep. Some records suggest that the great humid phase of the Sahara was already slowly unravelling, with a long-term trend toward aridity that began before 8.2 thousand years ago and continued long after. In that picture, the 8-2K event is more like a pulse superimposed on a downward slope, a bad decade or two in a century that was already getting harder. So what would that pulse have felt like if you were living in the green Sahara margin? Shrinking pasture means herds pressing closer together. Wells and waterholes that once supplied a few families now have to serve many more for longer into the dry season. Competition at these points can sharpen quickly, between different human groups, between domestic herds and wild game, even between species within your own flocks, as weaker animals struggle to reach the water first. As outer belts of usable land dry, migration corridors narrow. Paths that once arced widely across open grassland collapse into routes that hug remaining rivers, lakes, or seeps. That funnels movement through certain choke points, a particular pass, a chain of oases, a known pair of springs. Those places become strategic, socially and economically. Control over a lake's best inlet beach, or over the approach to a valley with reliable seeps, suddenly matters in a way it didn't when water was everywhere. For some groups, the answer may have been to lean into mobility, pushing farther south toward zones where the monsoon remained stronger, or west and east along belts that still caught enough rain. For others, it might have meant experimenting with new timing, arriving earlier at a basin to secure grazing, leaving later to catch the last flush of pasture, tightening the seasonal cycle. Archaeologically, we see hints of such adjustments in the distribution of sites. Some lake margins show intense use for a span and then an apparent lull, while other basins farther south or closer to enduring river systems pick up activity. Pottery styles and tool types shift in ways that might signal new contacts, new routes of movement as groups realign themselves with the changing availability of water and grass. Through all of this, the broader background kept sliding. The African humid period was not a stable plateau of greenness, it was a rise and fall. Over millennia, orbital changes were nudging monsoon strength downward. The Sahara was fated to re-expand. In that sense, the 82K event was not the cause of desertification, but a sharp elbow in a process already underway. Maybe in stories the elbow became a remembered episode, a time when certain lakes failed, when cattle thinned, when old paths north became roads of thirst and were quietly abandoned. From the vantage point of deep time, it looks like a blip in isotope curves and sediment layers. From the vantage point of families trying to keep herds alive on the Sahara's greener edge, it was another reminder that in this world, water could never be taken for granted, a lesson that would shape the societies growing along the Nile to the east, where a single river tried to buffer the moods of the sky and sea. Farther east, that reminder about water took on a different form. Along the Nile, people were not waiting for the sky to decide everything. They were watching a river. At 8.2 thousand years ago, the Nile was already an old system flowing through a young cultural landscape. Its waters gathered from the Ethiopian highlands and equatorial lakes, from seasonal rains that didn't care what was happening over the North Atlantic. Then it pushed north through desert, turning a narrow corridor of sand and rock into a ribbon of life. That geography created a strange kind of insurance policy. If local rains failed along the lower Nile, it didn't necessarily mean no flood. The river's annual rise was an integrated signal of weather far to the south and east, averaged over entire regions. A bad storm here, a shortfall there, could be smoothed out by the basin as a whole. Like a farmer who doesn't bet everything on a single field, a big river spreads risk. Hydrologists sometimes talk about rivers as low-pass filters. They blunt the day-to-day noise of rainfall, passing on the slower, broader patterns. To the people living along the floodplain, that filter felt like stability. You could count on a flood roughly once a year. You could learn where it usually stopped, which levees it overtopped, which sandbars stayed dry. Over generations, that rhythm taught people where to camp, where to sow, when to move their animals, when to fish the backwaters left behind as the waters fell. In a world of fickle monsoons and wandering lakes, the Nile must have seemed like a dependable beat under a complicated melody. But a filter doesn't erase a signal, it reshapes it. What the 82K cooling did to Nile floods is still debated. Some sediment records from the delta and from ancient flood basins show hints of change around this time. Layers suggesting lower discharge or shifts in grain size that might point to altered flood heights. Other cores from farther upstream show a more muted response, or changes that are hard to separate from the Nile's own internal swings. Part of the problem is that the Nile is fed by two very different climate systems. The Blue Nile and Atbara rivers are driven heavily by Ethiopian highland rains linked to the Indian Ocean monsoon. The White Nile carries water from equatorial regions where rainfall patterns have their own logic. A cooling in the North Atlantic might nudge both of these belts in subtle ways, but not necessarily in lockstep. One branch could weaken as another holds steady. The total flood at Aswan or farther north might wobble but not collapse. Some climate simulations of an 8.2K style event suggest modest reductions or increased variability in Nile discharge, rather than a simple uniform drop. That's not the kind of thing that redraws coastlines overnight. It's the kind of thing that redefines normal. Instead of a flood that reliably reaches a certain mark on the bank 8 years out of 10, maybe it only hits that line 5 years out of 10. Maybe there are a few more years where it arrives late, or peaks a little too early, or stalls below the fields your grandparents swore were safe. For communities starting to tie their seasons to the river, those small shifts matter. Archaeologically, we're looking at a subtle early landscape. This is long before pharaohs and pyramids, before hieroglyphic records of good and bad inundations. Much of what we know comes from scattered Neolithic sites along old channels and flood basins, camps with grinding stones, animal bones, early signs of plant use. Some scholars see a pattern in these layers around the centuries that bracket the 82K event. There are hints of changing site distributions, more concentration along certain floodplain zones, more occupation in areas where groundwater or residual floodwater would have lingered. There are suggestions of shifts in subsistence, with some groups leaning harder into fishing and wetland resources, others moving animals and camps closer to the flood's upper edge. But it's hard to say which part of that story belongs to climate and which belongs to people. Even in a perfectly stable environment, human groups shift settlement patterns as they discover better soils, new technologies, or more advantageous social arrangements. A new way of processing grain, a change in herd composition, a marriage alliance that opens access to a different stretch of river, all of these can leave traces that, thousands of years later, look like responses to something. When we peer back toward 8.2 thousand years ago, the Nile's archaeological record is a palimpsest of such changes, smeared together by floods, erosion, and later occupation. Separating a climate signal from political or social ones is like trying to hear a single instrument in a blurred orchestra. Even so, one theme keeps coming through: dependence on predictable water cuts both ways. As communities learn the Nile's rhythm, they could begin to plan beyond the next rainstorm, store surplus from a generous flood, build more permanent structures on the safest ground. Experiment with planting schedules that assumed a certain timing of the water's rise and fall. That planning is the seed of complexity. Once you can depend on a regular pulse of fertility, you can start to imagine specialists who don't gather food every day, gatherings timed to the flood's retreat, obligations to share or redistribute harvest from the best-placed plots. Over time, the logic of the river encourages calendars, rules, hierarchies, all the slow scaffolding of later statehood. But that same dependence turns variability into danger. If your social world is built around an expected flood, then a string of low inundations or a few years of strange timing doesn't just mean thinner harvests. It means stress on bargains and promises, rents that can't be paid in grain, agreements over shared fields that suddenly look unfair, people on the margins pushed to move or defer. In that sense, the Nile was a shock absorber and an amplifier at once. It buffered people from the worst of short-term rainfall swings, spreading risk across a vast basin. Yet it also concentrated consequence. When something did nudge its flow, whether from far-off ocean cooling, shifting monsoon belts, or slowly changing highland rains, the effects arrived not as scattered local failures, but as a coordinated jolt to everyone who had tied their life to the flood. Later Egyptian history would make this painfully explicit, recording famines and political crises during periods of repeated low inundation. In the early Holocene, we glimpse only the first outlines of that dynamic in the quiet movements of camps and the emerging reliance on floodplain resources. Beneath those movements lies a broader pattern that stretches far beyond the Nile. Wherever water becomes even a little bit predictable, in monsoon rivers, in snow-fed streams, in spring-lined oases, humans begin to stack their plans on top of that regularity. They turn pulses of water into rhythms of work, exchange and authority. The 8-2K event, with its delicate rearranging of rain belts and river flows, is one of the first times we can watch that relationship under stress. How a small change in the timing and reliability of water could ripple through societies that were just beginning to bet on order rather than chance. To follow that ripple, we have to look farther east again, to another great water system whose moods were tied at a distance to the same North Atlantic shock, the Indian monsoon and the lands of South Asia that waited each year to see whether its rains would keep their ancient appointment. If the Nile was like a slow, steady drummer, the Indian monsoon was more like a seasonal drum roll that decided, in a few weeks, how the rest of the year would go. In South Asia, everything leaned into that rhythm. By 8.2 thousand years ago, the early Holocene monsoon was on average stronger than today. Summers brought towering clouds inland from the Arabian Sea and Bay of Bengal, spilling rain across the Indus Plain, the Ganges Basin, and the uplands that rimmed them. For people experimenting with crops and herds in this landscape, the monsoon wasn't just weather. It was the calendar, but the monsoon does not live in isolation. It talks to the rest of the planet. Climate scientists use a dry word for this: teleconnections. It just means that what happens in one part of the climate system can echo far away through the shared machinery of air and ocean. The 8-2TA event began as a North Atlantic problem, a sudden pulse of cold, fresh water slowing down the great overturning circulation, cooling sea surfaces and shifting wind belts. That cooling, mostly in the northern hemisphere, changes the temperature contrast between land and ocean. And the Indian monsoon at its core is a response to that contrast. In simple terms, hot land, cooler ocean, strong monsoon make the northern hemisphere oceans cooler, reduce the land-sea temperature difference in summer, and the monsoon can weaken. Not necessarily every year, not everywhere, but in its average strength, its reach inland, its willingness to arrive on time. We don't have weather diaries from 8.2 thousand years ago in India or Pakistan. What we have instead are slow, patient witnesses, caves, lakes and layers of mud offshore. In certain limestone caves, drip by drip, minerals built up stalagmites, while people outside watch the sky. Tiny differences in oxygen isotopes inside those stalagmites seem to track how much monsoon rain fell above. Around the 8-2K interval, several South Asian cave records show brief shifts toward drier values, suggesting reduced monsoon intensity, or at least less moisture at that particular site. Lakes tell their own version. Sediment cores from some basins in the Indian subcontinent and the adjacent Tibetan plateau show changes in grain size, chemistry, or biological remains around this time. In a few cases, the evidence points toward lower lake levels or more evaporation, conditions you'd expect if monsoon rains faltered for a stretch. Out in the Arabian Sea and Bay of Bengal, marine sediments record changes in wind-blown dust, plankton, and land-derived material. Some cores show a subtle dip in indicators of river runoff and monsoon strength near the 8-2K mark, hinting that big river systems fed by monsoon rains may have briefly carried less water to the sea. None of these records is a simple rainfall gauge. Each is shaped by local geology, basin shape, and other climate quirks. And synchronizing them is hard. This is one of the main challenges in tying South Asia's story cleanly to the North Atlantic shock. Radiocarbon dates, uranium-thorium ages from speleothems, sedimentation rates in lakes and on continental shelves, all come with uncertainties that can add up to centuries. A wiggle in a cave record that looks like it lines up with the 8-2K cold spell might, in reality lead or lag it by a human lifetime or more. On top of that, the monsoon itself is not a single switch. It has branches and modes. Western India, the Indus headwaters, the Gangetic Plain, the Deccan interior, each feels the monsoon slightly differently, and local records can disagree about whether a given century was wetter or drier. So, climate modelers and paleoclimate specialists talk in terms of plausible teleconnections. Many simulations of an 82K style event show a weakened Indian summer monsoon for several decades to a century, especially in its western reach. The proxies, taken together, mostly lean in the same direction, some sign of disruption, not a collapse, layered on top of the monsoon's natural restlessness. What would that have meant on the ground? In parts of the Indus and its tributaries, early herding and cultivation were just beginning to take root. These weren't yet fully settled agricultural civilizations, but small communities testing the idea that certain plants, wild barley, wheat, millets, pulses, could be nudged into more predictable production. Goats, sheep, and cattle were being folded into mobile lifeways that still relied heavily on wild resources. In that context, weaker monsoon doesn't necessarily mean blank drought. It could mean rains starting later, ending earlier, or failing to push as far inland as usual. Maybe the lowlands still greened up, but upland pastures stayed sparse. Maybe the first sowing failed more often, and successful harvests leaned on a second, riskier planting. Maybe river flows became flashier, with shorter, more intense bursts and longer lulls. For farmers on the edge of domestication, those are not abstract changes. Shorter, less reliable rainy seasons make certain crops look risky and others more attractive. They might favour hardier grains, or encourage people to stick with flexible mobile herding rather than commit fully to fields. They might push camps toward places where moisture lingers a little longer, near springs, back-swamp depressions, or riverbanks that still flood, even in modest years. Archaeological traces from this time in South Asia are sparse and scattered. A few early sites in the northwest show mixed economies, wild plant use, animal herding, tentative cultivation. But the timelines are broad, and tying local changes directly to a century-scale climate event is difficult. Some scholars see hints of pauses or rearrangements in settlement patterns during the early Holocene. Others caution that the gaps may just reflect the accidents of preservation and discovery. So when we imagine South Asia under the touch of the 82K event, it's best to speak in possibilities. Perhaps a slightly weakened monsoon nudged communities to keep their options open, balancing crops with herds and wild foods. Perhaps it encouraged a wider seasonal circuit, following green patches as they appeared, rather than anchoring too firmly to a single field. Perhaps in a few marginal zones it turned promising cultivation experiments into cautionary tales told around evening fires. What the evidence does suggest is that the Indian monsoon was not immune to a far-off pulse of cold water in the North Atlantic. It heard the echo, if only faintly, and in a world where people were beginning to tie their hopes to the timing of rain, even a faint echo could matter. To see how that same distant shock might have rippled yet again, through a different set of seasonal winds and river systems, we have to look farther east to the shifting rain belts of East Asia and the communities learning to live beneath them. In East Asia, the seasons are written in moving bands of rain. Today we call it the East Asian monsoon. But for people on the ground then as now, it would have felt like the world breathing in and out. In summer, warm, moist air surges in from the oceans, drawn toward hot continental interiors. In winter, the pattern flips. Cold, dry air spills out from the land, pushing storms seaward. It's a system that lives on contrasts between land and sea, warm and cold, high and low pressure. And because of that, It is exquisitely sensitive to anything that changes those contrasts, even far away. The 8-2K event, born from cold freshwater in the North Atlantic, didn't just cool a few seas near Greenland. It nudged the entire Northern Hemisphere's temperature gradients, and with them the great belts of wind and rain. Climate models that simulate an 8-2K style freshening often show subtle shifts in the East Asian summer monsoon, a slightly weaker pull of moist air inland, or a southward displacement of the main rain band, sometimes called the Mayu or Bayou front. But models are only half the story. The rest comes from the quiet record keepers of East Asia's landscape. In southern China, stalagmites grew in dark cave chambers, while outside the first farmers were testing millet, rice and root crops in patches of cleared land. Oxygen isotopes in some of these speleothems show brief anomalies near the 8.2 thousand year mark, small swings that suggest changes in the amount or seasonality of rainfall. In a few well-dated cave records there's a hint of drier conditions, or at least a shift toward rain arriving in shorter, more intense pulses. Farther north, in Loess plateaus and lake basins, layers of dust and mud record the waxing and waning of moisture. Grain size in Loess can tell you how strong the winter monsoon winds were. Lake levels hint at how generous the summer rains became. Around the 8-2K interval, some northern Chinese lakes show signs of lower stands or more evaporative conditions, while others show little change at all. A patchwork, not a single verdict. Offshore in the Yellow Sea and the East China Sea, marine sediments preserve bits of pollen, riverborne silt, and the remains of tiny marine organisms that respond to freshwater input and surface temperatures. A few cores show modest dips in river discharge proxies near this time, as if the Yangtze and other systems briefly slackened their flow. Put together, the picture is not one of a dramatic monsoon collapse, but of a system twitching, rain belts shifting slightly, some regions drying a bit, others perhaps even gaining moisture as the main storm tracks wobbled. For early cultivators from the Yellow River to the lower Yangtze, those twitches could still matter. In the north, along the Lewis-mantled valleys of the Yellow River, millet was becoming the grain of choice. Millets are tough, they grow fast, tolerate poor soils, and can cope with short, erratic rainy seasons better than many crops. But even millet needs a minimum window, enough warm days with moisture in the soil to germinate, tiller, and fill its seeds. If the 8-2K event trimmed a few weeks off the dependable wet season, or pushed the main rains later into the summer, that could have squeezed the odds. First plantings might fail more often if early showers didn't arrive. Farmers, or more accurately foragers dabbling seriously in cultivation, might have leaned harder on multiple sowings, staggered over time to catch at least one successful pulse of rain. Some zones on the northern margins, already close to the threshold where dry steppe turns to true desert, might have found millet cultivation just that bit more precarious. In such places, people may have hesitated to commit fully to a farming life, keeping hunting and gathering, and perhaps mobile herding, firmly in the mix. Farther south, in the middle and lower Yangtze Basin, rice was entering the story. Early rice at this time was not yet the irrigated paddy rice that would later cover the region in terraces and ponds. It often grew in naturally wet settings, floodplains, back swamps, lakeshore margins, where seasonal waterlogging created a niche. Here, the key was not just how much rain fell, but when it fell, and how long surfaces stayed wet. If the summer monsoon weakened slightly, but the main rain belt lingered longer over the middle Yangtze, some wetlands might have stayed just as soggy, or even become more favourable. In other microregions, a shorter inundation period might have made proto-paddy experiments more difficult, encouraging people to keep rice as one component of a broader wetland foraging strategy rather than a staple. This is where microregional resilience comes into focus. East Asia in the early Holocene was not a uniform plain waiting for a single climate verdict. It was a mosaic, broad river corridors with multiple channels and backwaters. Lowland wetlands that trapped moisture even in drier spells, upland basins catching local rains, forested hills that shaded springs and seepage zones. If the main summer rain belt shifted 50 or 100 kilometers, entire microregions might have experienced a different reality. A north-facing valley could keep its snowmelt and seeps longer, feeding small plots, even when the wider plain dried early. A floodplain with frequent overbank flows might stay productive despite a modest drop in overall rainfall, because each flood still recharged its soils and ponds. Communities tuned to these fine-grained differences had options. They could move camps a day's walk toward a more reliable tributary. They could favour fields on slightly heavier soils that held moisture longer. They could increase their use of wetland plants, fish and shellfish when grain harvests disappointed. From the perspective of climate science, though, tracing the 82K signal in East Asia is delicate work. Dating uncertainties in cave records, lakes and offshore sediments mean that a wiggle that appears to align with the North Atlantic event might in reality be offset by centuries. Different proxies also respond to different aspects of the monsoon: total rainfall, seasonality, storm intensity or temperature. So their stories don't always match cleanly. Some sites hint at drying, others at little change, and a few even at temporary wetting. That spatial complexity is not a failure of the data. It is a clue to how the monsoon actually behaves, as a moving, shifting band of convergence, not a uniform blanket of rain. So, when we imagine East Asia during the 82K event, the safest picture is a subtle one. Rain belts nudged southward or weakened in some summers. Growing seasons shortened slightly in marginal zones, pushing millet farmers to juggle risk and redundancy. Rice pioneers in the wetter south watched water levels with even sharper attention, learning which patches stayed wet just long enough and which dried too soon. In between, countless microhabitats softened the blow, turning a hemispheric climate glitch into a series of local puzzles rather than a single catastrophe. Those puzzles were answered in different ways by mobility, by diversification, by tinkering with where and when to plant. And as the decades passed and the climate drifted back toward its early Holocene norms, the lessons people had learned about thresholds and variability did not disappear. They stayed in memory, encoded in habits and stories, as East Asia's rain-fed experiments with cultivation slowly matured into the more settled farming lifeways that would later anchor entire civilizations. Meanwhile, on the far side of the planet, closer to the source of the cold pulse itself, other communities were facing a different version of the same global tremor. To see how the 82K event looked where the trigger was pulled, we have to cross back over the oceans to the Americas. If the 8.2 thousand year event had a home address, it would be in the high latitudes of North America. Here, at the end of the last ice age, the continent still carried scars, enormous ice sheets wasting away, and behind their retreating fronts, vast proglacial lakes pressed up against walls of ice and moraines. Among them, Lake Agassiz and its successor, Lake Ojibwe, were giants, inland seas stretched across what is now central Canada and the northern United States. For thousands of years, these lakes had been mostly stable, held in place by the geometry of ice and rock. But around 8.2 thousand years ago, something changed. Ice dams weakened, outlets shifted, and a colossal volume of cold freshwater found a new escape route, racing toward the North Atlantic through channels that roughly follow today's St. Lawrence and Hudson Bay drainage systems. From orbit, it would have looked like plumbing on the ground. For anyone living anywhere near the outflow corridors, it would have felt like the world's rivers suddenly forgetting their old habits. The immediate climate response near those routes was not subtle. Models and regional reconstructions suggest that eastern and northeastern North America cooled by a few degrees, especially in winter. Some areas likely saw longer snow seasons, later thaws, and a sharper divide between short, cool summers and drawn-out, chilly springs and autumns. Ecosystems responded on their own slow but relentless clock. Pollen preserved in lake sediments from eastern Canada and the northeastern United States shows brief reversals in the general warming trend of the early Holocene. Forests that had been marching northward paused or briefly retreated. In some sequences, boreal species like spruce and fir regain ground at the expense of temperate hardwoods, a quiet testimony to cooler, perhaps slightly drier conditions. Along coasts, the picture was even more complicated. On one hand, global sea level was still rising as ice sheets melted, slowly drowning older shorelines. On the other, the sudden redistribution of water and ice changed how the Earth's crust flexed. Near the old ice margins, land was still rebounding upward from the weight of the vanished ice sheet. Farther away, different regions sagged slightly under the shifting loads of water. For people living near bays and river mouths, the shape of estuaries and tidal flats, the reach of brackish waters, the timing of fish runs, all could have changed within a few generations. But how would such a pulse register in human lives here? In most of the Americas at this time, communities were not farmers in the Near Eastern sense. They were mobile or seasonally settled hunter-gatherers, sometimes with early experiments in plant management, but still deeply tied to wild resources. That did not make them less sensitive to climate, it made them differently sensitive. Farmers feel climate shocks most when they lose control over a narrow window, a few weeks of planting, a single harvest. Mobile foragers live on a broader portfolio. They can shift hunting territories, emphasize different fish runs, move camps upslope or downslope, spend a few years favouring nuts over salmon or vice versa. Climate pulses show up not as a single failed harvest, but as subtle reshufflings of seasonal rounds. A river that freezes longer, a berry crop that becomes less reliable, a caribou herd that shifts its calving grounds beyond a familiar pass. The proxy records we have from North America hint at such changes, without spelling out the stories in full. In Greenland's ice, the 82K event is razor sharp, a sudden drop in oxygen isotopes, a clear signal of cooling. South of the ice, the signal becomes blurrier. Lake Varve records from places like Hudson Bay lowlands and parts of New England show changes in sedimentation around this time, suggesting shifts in runoff, freeze-thaw cycles, and perhaps storminess. Pollen sequences in the Great Lakes region capture that short-lived return to more boreal-like vegetation. Speleothems in a few North American caves record slight isotopic excursions, consistent with altered precipitation patterns. Offshore in cores taken from the North Atlantic margin, the story of the flood is written in the chemistry of tiny shells, a spike in freshwater indicators, a dip in sea surface temperatures, subtle changes in the species that thrive in colder, less salty water. It is from these lines of evidence that researchers reconstruct the massive meltwater pulse and link it to the cooling that rippled through the hemisphere. On land, however, tying those physical changes to specific cultural transitions is harder. Archaeological sequences in eastern North America, around 8.2 thousand years ago, do show developments, shifts in stone tool styles, changes in site locations, adjustments in how people used coastal versus inland resources. In some regions, there are hints of increased mobility, or of camps clustering near especially reliable wetlands and river crossings. But those shifts unfold over centuries, sometimes a millennium or more. They overlap with long-term processes that were already underway, the spread of particular forest types, the gradual flooding of coastal plains, the slow accumulation of knowledge about plants that would later be domesticated. Dating uncertainties mean that an apparent change in material culture that looks close to 8.2 thousand years ago could easily be a few centuries off from the climate pulse itself. So when we look at the Americas, even at the very place where the trigger was pulled, the most honest picture is one of gentle pressure rather than instant transformation. The Great Lakes spilled, the North Atlantic cooled, winters in the northeast lengthened, forest mosaics shifted a little back toward cold-tolerant species. Estuaries changed shape as land and sea reorganized themselves. Hunter-gatherer groups, already experts in reading seasonal cues, adjusted their calendars and territories, not in panic, but in the same pragmatic way they had weathered countless smaller anomalies. The flood narrative is real in the physical sense, a geologic rearrangement of water that disrupted a major ocean circulation pattern. Its imprint on climate is clear in ice, mud, and microfossils. Its imprint on culture, however, is softer, braided into a tapestry of other forces and local histories. The 820K event nudged the stage on which early American societies were improvising, but it did not write their script for them. Their responses, like those in the Near East, in Europe, in Africa, and across Asia, were filtered through lifeways that were already flexible, already diverse, already tuned to a world where change was the rule rather than the exception. When we talk about the 8.2 thousand year event disrupting early societies, we're really talking about patterns we see in dirt, bones, and broken stone. Archaeologists don't get eyewitness accounts, they get layers. So what, in practice, counts as a signal of disruption? One kind of signal is abandonment. You excavate a settlement that has been occupied for generations, thick floors, rebuilt hearths, layers of trash, and then suddenly nothing. The uppermost layers show a last sweep of activity, a final scatter of tools, maybe a few storage pits left half-filled. Above that, clean sediment, wind-blown sand, silt washed in by floods. No more hearths, no more house posts. It looks as if people walked away and never came back. Another kind of signal is destruction. Burn layers. A dark band of charcoal and ash running across a site, sealing the last occupation under a blanket of fire. Sometimes it's obviously intentional. Collapsed walls, melted daub, a whole village burned in one intense episode. Sometimes it's patchy and ambiguous. A few burned structures, a lot of unburned ones. Fire can mean warfare, arson, rituals of closure. It can also mean a cooking accident on a windy day. Then there are the quieter signals, the bones of animals, the shells of mollusks, the seeds and charred grains in old hearths and storage pits. When climate shifts, the menu often changes. In some regions around 8.2 thousand years ago, faunal assemblages show fewer large animals and more small game, fish or birds. In others, you see a rising reliance on particular hardy species, drought-tolerant gazelle instead of water-loving cattle, or shellfish that thrive in cooler, more brackish estuaries. These switches can hint at altered landscapes or stressed herds. Storage is another important clue. Archaeologists pay close attention to when societies begin to invest more heavily in pits, silos, jars, granaries. An increase in storage capacity can signal growing surplus. It can also signal rising risk. If harvests become less predictable, if winters stretch out unpredictably, people hedge their bets by storing more food in more secure ways, sometimes under the floor, sometimes in communal facilities with thicker walls and tighter locking mechanisms of stone and clay. Taken on their own, each of these patterns can look like disruption. But that's where a core problem in archaeological reasoning appears: equifinality. Equifinality is a technical term for a simple idea. Different causes can produce the same outcome in the record. A village might be abandoned because rainfall failed for decades, or because a rival group attacked, or because a river changed course, making the site less convenient, or because a new, more attractive location opened up nearby with better trade opportunities. Look only at the empty houses, and all those stories look the same. A burn layer might record a climate-driven wildfire racing into a settlement at the end of a long drought. It might record a raid. It might record a controlled burning of old structures in a planned relocation. Ash is ash, charcoal is charcoal. The motives behind the flames don't fossilize easily. Shifts in animal bones can signal changing climate, but they can just as easily reflect new hunting preferences, new taboos, new technologies that make different prey more profitable. Even an increase in storage could mean either stress or prosperity, or both at once. Because of equifinality, archaeologists lean heavily on timing. If a cluster of abandonments, burn layers and subsidence shifts all fall within the same narrow window as a known climate pulse, the case for disruption gets stronger. But narrow in our terms is not always narrow in human terms. Radiocarbon dating, the workhorse of early Holocene chronology, does not give a single year. It gives a range of possible dates, often spanning several decades, sometimes more than a century. Those radiocarbon ages then have to be calibrated because the amount of carbon-14 in the atmosphere has varied through time. Calibration curves themselves are built from other archives, tree rings, corals, speleothems, each with their own uncertainties. By the time all that is folded together, an event in the archaeological record that we call about 8.2 thousand years ago might have actually happened a few human generations before or after the peak of the climate signal in the ice cores. And decades matter. For us, looking back, the 82K event is a single blip, a narrow notch in a graph. For people alive then, it was a cluster of hard years, maybe a lifetime where the weather felt a bit off, the rains unreliable, the winters longer, a village founded at the start of the cold spell and abandoned 50 years after its peak would, in lived experience, be a community forged under that new pattern. In our lab books, it might look a little too early or a little too late to line up neatly. This is why single-site stories are always fragile. A single abandoned village can seduce us into neat narratives. To test those narratives, researchers try to move beyond one site, one type of evidence. They build multi-proxy, multi-site pictures. Multi-proxy means combining different kinds of records, pollen and lake sediments for vegetation and moisture, oxygen isotopes in speleothems for rainfall patterns, microcharcoal for fire, animal and plant remains for diet, settlement patterns for where people chose to live, architectural changes for how they invested in place. Multi-site means looking across a whole region. Do several valleys show synchronous abandonments? Do coastal and inland sites shift their emphasis at roughly the same time? Does the appearance of more storage in one zone match a decline in another that might have become less reliable? When signals line up, when a drying trend in cave isotopes matches a shift in pollen, matches a spike in storage pits, matches a thinning of herds in the bones, then we can say, with cautious confidence, that something more than coincidence may be happening. Even then, the language stays careful, consistent with, compatible with, may reflect. The most responsible reconstructions are always hedged, because one more site, one better date, can complicate the picture. And we also have to live with silence. For large parts of the world around 8.2 thousand years ago, the archaeological record is thin. Sites haven't been found or haven't survived or haven't yet been dated closely enough to see fine-grained change. In some regions, erosion has stripped away the very layers we'd most like to examine. In others, deep alluvium or modern cities simply hide what's underneath. It's tempting to say, nothing happened here, no disruption, no response. But that temptation misreads the nature of the evidence. Absence of evidence is not evidence of absence. No burn layers does not mean no fires. No visible abandonments does not mean no quiet relocations over a generation or two. No spikes in storage jars does not mean people weren't thinking hard about risk. They might simply have been storing food in ways that leave little trace. The 82K event is clearest where nature kept meticulous records, in ice cores, in varved lake sediments, in corals and speleothems. Human records are messier, patchier, and always incomplete. Reading disruption in them is less like watching a documentary and more like listening for a faint echo in a noisy room. As we turn to human responses, mobility, networks, storage, social rules, it helps to keep that in mind. We are not looking for a single global pattern stamped neatly on every society, but for clusters of hints, places where the climate pulse seems to have pushed existing trends a little harder or nudged fragile systems past thresholds they were already approaching. The microscope can sharpen our view. It cannot guarantee a simple story. If you strip away the pottery styles and the stone tool typologies, one basic survival strategy shows up again and again in the early Holocene record. People moved. Not all at once, not in dramatic migrations out of storybooks, but in adjustments of where and when they went across the landscape. Shifts in winter camps, new summer grazing areas, villages that seem to hop a valley over or inch closer to a river or stretch out along a coast. Mobility was not a last resort. It was a built-in feature of how many early communities managed risk. For hunter-gatherers, this is obvious. Their entire economic logic is based on following animals, tracking plant seasons, moving between river, forest and upland as resources wax and wane. Around 8.2 thousand years ago, in regions that cooled and dried, some groups seemed to widen their annual circuits. Sites that had once been used briefly now show thicker layers, suggesting longer stays, perhaps because other patches had become less reliable. In other places, small, short-lived camps pop up in areas that had been little used before, hinting at experimental forays into new niches. Farmers look more settled on paper, but even early agriculturalists treated mobility as an option. Fields could be shifted, herds could be walked. In parts of Anatolia and the Levant, there are phases where permanent villages thin out, while smaller seasonal sites, sometimes with corrals but little architecture, become more common. One way to read this is as a partial return to flexibility when rainfall patterns grew less trustworthy. Keep the orchards and fields where you can, but loosen the overall attachment to one fixed spot. Overlaid on this movement were networks. If mobility is a way of smoothing risk over space, exchange is a way of smoothing it over people. Archaeologists see these networks in obsidian from distant volcanoes, in shells from far-off coasts, in distinctive stone types or pigments that show up hundreds of kilometers from their sources. Around the time of the 82K event, in several regions, the reach of these materials expands or contracts. Some valleys that had been tightly connected seem to drop out of long-distance circuits, others suddenly plug in. One interpretation is that when local harvests or hunts failed more often, ties to other groups became more valuable. A bad year in one catchment could sometimes be balanced by a better year somewhere else. Gifts, marriage alliances, and ritual exchanges moved, not just pretty things, but access to grazing, to fishing spots, to stored grain, to a place at someone else's hearth if your own home place faltered. Under that kind of pressure, social ties were as important as tools. A community with brilliant irrigation ditches but few friends was in some ways more vulnerable than a technically modest group woven into a dense web of obligations. When rains shifted and herds thinned, what mattered was not only who had the better sickle, but who could call on help, who could relocate without starting entirely from scratch, whose children had in-laws upriver or along the coast. This brings us to the idea of refugia. Refugia are places that stay relatively buffered when conditions around them deteriorate. They don't escape the climate pulse entirely, but they soften it. A spring that flows even in dry years, a north-facing slope that keeps moisture a little longer, a coastal lagoon that still teems with shellfish when inland pastures crisp. In the 8-2K interval, some zones seem to act this way. Lakes with groundwater inputs hold their levels while shallower basins dry. River valleys fed by glaciers or stable aquifers continue to flow when rain-fed streams become seasonal. Coastal shelves exposed by lower sea level offer broad new foraging grounds. In pollen records, these refugial pockets can show more continuity in vegetation than surrounding hills or plains. People noticed. They may not have spoken of hydrogeology or monsoon weakening, but they learned through experience and stories that some landscapes rode out the bad years better than others. Over generations, such places drew in more seasonal visitors. A handful of families might become dozens during lean times. A small fishing camp might grow into a more permanent village at the junction of river and sea, precisely because it could be counted on when upland fields failed. Rivers, coasts, uplands, each offered a different kind of safety and a different kind of risk. Rivers tied you to water and fertile soils, but also to floods and to competition over narrow corridors of green in a browning world. Coasts gave you fish, shellfish, sea mammals, and access to multiple ecological zones within a day's walk, but storms and changing sea levels could redraw the map under your feet. Uplands could catch extra rainfall, offer cooler temperatures, and harbour drought-resistant plants. Yet winters there were harsher and seasons shorter. The pattern that emerges is not of people passively enduring a climate shock, but of people using the full repertoire they had, moving when they could, staying put where it made sense, tightening some social bonds and maybe letting others lapse, gravitating toward refugia when the wider landscape grew more capricious. In the next layer of response, something else begins to show up more strongly, not just where people went, but how they tried to trap time itself in pits, jars, granaries, and how those strategies quietly altered power and inequality. If mobility and networks were about spreading risk, storage was about a different gamble altogether. Instead of outrunning bad years across space or smoothing them across relationships, storage tries to pull a piece of the future into the present and hide it away. Grain in a pit, dried meat in a basket, nuts cached in jars tucked under a house floor, food taken out of the uncertain flow of seasons and held, if all goes well, under human control. In a climate pulse like the 8-2K event, that gamble starts to look increasingly attractive. Evidence for storage is patchy and regional, but in several parts of the Near East and surrounding zones, archaeologists begin to see more deliberately constructed silos, lined pits, and clusters of large containers precisely in the centuries around and after the cooling. Earlier households might have a few baskets or bins. Later phases show substantial facilities, plastered chambers, deep bell-shaped pits, thick-walled jars sunk into floors. Some of this is just what you'd expect from maturing farming economies. But when you line it up with pollen records showing more variable harvests, or with lake cores hinting at irregular rainfall, a pattern emerges. In a world where one year's crop might be fine, and the next sharply reduced, the ability to store surplus becomes a central climate strategy. And storage changes more than just the menu. Once food is concentrated in particular places, it becomes much easier to see who controls it. A hillside covered in wild stands of grain is hard for anyone to monopolize. 10 clay silos in the middle of a village courtyard, on the other hand, can be locked, guarded, counted and allocated. At first, control might simply mean responsibility. Someone has to maintain the bins, patch the plaster, keep out rodents, decide when to open which pit so the grain doesn't all spoil at once. In many small-scale societies, this kind of role is embedded in kinship or ritual rather than framed as power. The owner of the granary is a lineage elder or a custodian acting on behalf of an ancestor cult, rather than a boss in the modern sense. But when bad years come more often, that custodial role can quietly acquire sharper edges. Imagine a run of lean harvests in a village that has begun to rely on stored grain. Decisions about who eats how much, when to dip into reserves, and which obligations to honour first cease to be abstract questions. They are life and death negotiations. Households with their own storage might bargain from a position of strength. Those without must lean harder on social ties, promises and debts. Under those conditions, inequality has fertile ground. Households that produce a bit more surplus, or that happen to sit next to especially reliable fields or springs, can store more. They can extend loans in grain or seed. They can demand labour, marriage alliances, or access rights in return. Over time, differences in storage capacity and in the credibility of one's promises may calcify into differences in status. Who eats first at feasts? Who leads rituals to protect the harvest? Whose word carries more weight in deciding when the granary doors open? In several early Holocene sites, archaeologists find storage features that are not neatly tied to individual houses, but sit in semi-public spaces. Large pits or structures that seem too big for one family. One way to read these is as communal reserves, grain held in common, perhaps under the aegis of a council, a chief, or a ritual organization. The 8-2K disturbance would have made such arrangements both more appealing and more contentious. Managing shared storage requires rules. Who contributes and how much? Who can withdraw and under what circumstances? How do you prevent someone from quietly skimming off the top? These questions lend themselves to meetings, to agreements, to taboos. Maybe certain doors can only be opened on particular days. Maybe a ritual is required, with witnesses, songs and offerings, every time the big jars are unsealed. Maybe infractions are not framed as theft from neighbours, but as insults to the ancestors or to the spirits of the fields. Repeated shocks give these rules teeth. If a community goes through not just one bad year, but several episodes of uncertainty over a few centuries, the stories about what worked last time strengthen. A ritual that seemed optional becomes necessary. A rule about how much grain young families must contribute starts to feel like tradition, then like law. People begin to say, not we decided this, but this is how it is done. Here, leadership and coordination can crystallize. The person who officiates the opening of the communal pit, who announces the redistribution schedule, who mediates disputes when someone claims they were shortchanged, that person or that group begins to occupy a distinct social niche. They may be elders, ritual specialists, or simply those with reputations for fairness and knowledge about rains and soils. Climate stress alone does not create them, but it increases the premium on their skills. Similarly, in villages experimenting with small irrigation systems or with managing access to reliable springs during dry spells, some hand has to coordinate. Men and women who can organize cleaning of channels, schedule turns for watering, or negotiate with upslope and downslope neighbours acquire a kind of practical authority. Around 8.2 thousand years ago, a number of riverine and oasis settlements show traces of more formalized layouts, regularized fields, shared works, constructions that would have required collective labor. Behind those works, even if we cannot see them directly, were negotiation and leadership. None of this was mechanically determined by climate. Institutions can emerge from many sources, from charismatic individuals, from religious revelations, from slow demographic growth, from the demands of long-distance trade. The 8-2K event was not a puppeteer pulling strings, but it was one more weight on the scales, one more set of pressures pushing communities to formalize what had once been flexible, to codify what had once been improvised. Over generations, that codification is what we might call rewiring. Not a sudden revolution, but subtle shifts in how households relate to one another, how decisions are made, how obligations are remembered. A little more food moves through shared pits instead of private baskets. A few more arguments are settled by reference to common rules instead of ad hoc bargaining. A few more people come to specialize in managing water, grain, and the rituals that hover around them. By the time the climate settled back toward a new normal, some of these arrangements would have become part of the background, taken for granted, wrapped in story and ceremony. In the next turn of our story, we'll look more closely at that layer of meaning, the myths, rituals and memories that helped communities live with, and make sense of, a world that could change so suddenly. Rules alone don't hold a community together. To really stick, they need reasons, stories about why things are done this way and not that way, about what happens if you stop. After a climate shock like the 8-2K event, those reasons almost certainly multiplied. Imagine living through a decade when the rains that used to come in late spring now hesitate, then arrive in a cold rush, or fail entirely. When a river that always flooded gently instead surges too high one year and barely at all the next. You don't have thermometers, or ice cores, or ocean circulation models, but you have eyes, memory and fear. So people look for patterns. Did the cold wind come the year we neglected the ancestor shrine? Did the last failed harvest coincide with a dispute over a boundary stone? Was the only field that did well the one near the old burial mound where offerings are sometimes left? Out of partial memories and coincidences, linkages begin to form, and in small-scale societies, the medium for those linkages is often ritual. In the archaeological record, we can't hear the words of the prayers or the tone of the songs, but we do sometimes see the shadows they cast. There are settlements where, right around the time the climate records show increased variability, we find unusual deposits, layers of broken but carefully selected animal bones, caches of intact, unused tools arranged together, whole vessels placed in pits, sometimes upside down, then covered and never disturbed again. Not trash, but offerings. We see communal spaces taking on clearer forms, plazas cleaned more regularly, buildings that don't look like houses, too big, too empty of everyday debris, placed at the centre or slightly apart from domestic clusters. In some regions, certain rooms are repeatedly replastered, painted and burned, then buried and built over again, as if the very act of renewal is part of the point. Feasting leaves its own fingerprints, outsized hearths, dense accumulations of animal bones from many individuals of the same species, big serving vessels far too large for one house. At some sites there are repeated episodes of this kind of abundance followed by a pause, then another burst, as if communities periodically gathered to affirm something about who they were and how they would face uncertainty together. Boundary markers may also speak to this search for order. A line of posts renewed over generations, a line of stones dividing one field from another becoming more formal, more monumental, perhaps accompanied by small offerings. Sacred groves or special trees spared when others are cut, standing at thresholds between fields and wild land, between ours and theirs. Marking and remarking space is a way of asserting stability when the seasons refuse to cooperate. Could some of these shifts be tied to the 8-2K disturbance? Possibly. Climate proxies and archaeological phases sometimes line up in suggestive ways. A new kind of communal building appears just after a local drying pulse. A surge in animal offerings coincides with pollen hints of stressed crops. But the line from climate to ritual is never straight. People invent ceremonies for many reasons, to cope with disease, to manage conflict, to honour ancestors, to celebrate trade partnerships or marriage alliances, or simply because a charismatic dreamer convinces others that a new practice is needed. When we see an increase in offerings or a change in burial treatment around the time of a climate event, it is tempting to say, this is the ritual answer to the cooling. That might be true. It might also be coincidence, or a response to some other local pressure we can't see. Archaeologists tread carefully here. They can map patterns, trace what appears before and after, but they can't with any certainty read a drought into every burnt layer, or a frost into every new shrine. At best, they can say, in times of recognized environmental stress, societies often elaborate rituals of protection, thanksgiving, and renewal. The 82K event fits that broader tendency, but it is one thread in a much larger tapestry of meaning-making. Still, that tapestry has a remarkable property. It doesn't just reflect the past, it stores it. This is what scholars call cultural memory. A story about the year the river walked away can be told for generations after the river returns to its usual course. A prohibition against planting in a low-lying hollow, because the spirits punish those who do, may encode a practical lesson about flood risk learned painfully long ago. A festival at the end of the hungry season, with strict rules about sharing, can carry the memory of a famine even when no one alive remembers the original event. Cultural memory doesn't need writing. It lives in rituals repeated at specific times, in songs with odd verses that no one fully understands. In the particular way a house must be oriented, or a field must be divided. Much of it may be opaque to participants, yet still shapes what seems thinkable when new risks appear. After something like the 82K event, communities that survived would have come out of it with stories, tales of the bad winters, the empty granaries, the miraculous field that didn't fail, the stranger who arrived with a new seed or a new prayer. They might frame the cold years as punishment, as a test, as the work of distant powers, or as a cycle that comes and goes. Each framing matters for the future. If the shock is remembered as pure misfortune, perhaps the best you can do is diversify your fields and strengthen your exchange networks. If it is remembered as a consequence of neglecting certain rituals, then maintaining those ceremonies becomes non-negotiable, a kind of insurance policy. If it is seen as part of a great cycle of death and rebirth, communities may come to expect periodic collapses and be psychologically prepared to rebuild. These narratives guide real decisions, where to build, what to store, whom to trust, when to move. They also guide how much flexibility people feel they have. A rule wrapped in sacred narrative is harder to change, even if the climate baseline slowly shifts again. Some scholars have wondered whether the 82K event could lie behind much later myths of a world that suddenly turned hostile, stories of great colds, of vanished rains, of societies forced to move and remake themselves. The timing is awkward for a direct inheritance into the mythologies we know, but the pattern of instability followed by renewal, of fall and reconstruction is strikingly common. And somewhere in the middle of these deep time puzzles, it's worth pausing on a more recent mystery. If you find yourself curious about other ancient puzzles we can't quite explain, enigmatic ruins, lost rivers, unexplained sky events, there's a book about 12 of these mysteries available on our website. The link is in the description if your waking self wants to explore further. In the early Holocene, though, the script was being drafted for the first time. Communities experimented not only with granaries and canals, but with ceremonies to open and close them. They experimented with who could speak to the powers that governed rain and growth, with which ancestors were remembered and which were allowed to fade. They tested taboos about cutting certain trees, fishing in certain pools, marrying across certain lines. The 82K event did not write those rules for them, but it likely sharpened the stakes of getting them right. A community that believed its rituals had carried it safely through the cold pulse might double down on them, elaborating details, tightening requirements. A community that felt its old practices had failed might be more open to radical prophets, to imported gods, to new ways of marking boundaries and seasons. Either way, the memory of disturbance becomes part of the mental landscape. By the time the climate settled into a new, somewhat more stable regime, many of these stories and rituals would have aged into tradition. Children would grow up never having known the shock itself, but knowing that this is how our people guard the harvest. This is where we never build. This is the song we sing when the first cold wind blows. And so a brief, sharp flicker in the climate record becomes smeared out in cultural time, not as a single event, but as a background sense that the world can, without much warning, change its mind. In that sense, the 82K event may have been one of the early tutors in a lesson humanity keeps relearning, that stability is precious, precarious, and always somehow tied to the ways we remember and retell our own past. In the final part of our journey, we'll step back from the details and ask what this ancient cold snap really shows us about climate and civilization, and what it can't tell us no matter how closely we stare into the ice. So, after all this, what does that brief shiver in the Holocene actually tell us? First, the physical outline is fairly clear, at least in broad strokes. Somewhere around 8,200 years ago, a lot of meltwater that had been dammed up in the remnants of the North American ice sheets found a way out. It rushed, not as a single Hollywood wall of water, but as a geologically sudden flood into the North Atlantic. All that cold, fresh water diluted the salty surface, made it lighter, harder to sink. The great overturning circulation of the Atlantic slowed like a pump losing its prime. When that happened, heat that had been steadily moved northward began to bottleneck further south. Regions around the North Atlantic cooled by a few degrees. Storm tracks shifted. Monsoon systems on the other side of the world wobbled. In some places, this meant colder, drier years. In others, wetter winters or sharper seasons. In a few, not much change at all. It wasn't a global ice age, it was a pulse, a complicated rearrangement of where heat and moisture went. Against that backdrop, the human story looks less like a single dramatic collapse, and more like a series of regional rearrangements. Some farming communities shrank, moved, or fused with neighbours. Others doubled down on storage, irrigation, and social rules to manage risk. Foragers tilted their territories, shifted hunting grounds, added new plants or animals to their diets. Networks frayed in some directions and thickened in others. A few places were probably abandoned. Others may have quietly flourished in newly favourable niches. What we see again and again is adaptation and reorganisation, not a single moment when civilization almost died. And there is a lot we don't see. Ice cores tell us about temperature and atmospheric chemistry, but nothing about fear or hope or argument. Lake sediments and tree rings sketch rainfall and drought, but not who married whom to keep a trade route open. Potsherds, bones and burned layers hint at diet, ritual and conflict, but rarely come with dates precise enough to say, this village failed because of that cold decade. This is why paleoclimatologists and archaeologists lean on multiple lines of evidence, and why they speak in terms like likely, consistent with, and one possible interpretation. The closer we look, the more the 82K event refuses to be a simple parable. What it does offer is a quiet, powerful reminder. Early farmers and foragers were not passengers in the face of climate. They were entangled with rivers and rain belts and ocean currents, yes, but also with each other. They moved, they bargained, they experimented with seeds and stories, with ditches and deities. Out of a short, sharp climate wobble emerged not a single outcome, but a branching set of paths that would, over millennia, feed into the long arc of towns, kingdoms, and the worlds we inherit. We live at the far end of that arc, carrying genomes and memories shaped by countless earlier shocks. The 8-2K event is one small reminder that abrupt change is part of our deep past, and that resilience, cooperation, and creativity are too. If you've drifted this far with us and your eyes are still open, you can gently help this channel grow by liking this video, leaving a comment, and subscribing for more journeys into deep time. If you're awake enough to type, tell us where you're listening from. It's always fascinating to see this scattered modern network of ears. And if you ever wonder how to best support what we do, the simplest way is to listen on Spotify. The link is in the description. For now, let the thought settle that long before our histories were written, people were already learning how to live with a restless sky.